Deputy Director and Director in Charge, and Sujit Sir, HOD Chemistry Department, and distinguished faculty members from the NIT Academy. A warm good morning to all. It's with immense pleasure today we are starting the 7-day workshop on the data acquisition and analysis on NMR and HRMS, sponsored by SERB under the Accelerate Vignan scheme. At the outset, I extend a warm welcome to Dr. P.S. Sadidevi, Director in Charge and Deputy Director NITC, to the inaugural function and as well as to the. Now I welcome our HOD, Dr. A. Sujit, to this workshop. Sujit sir, a warm welcome. I also extend a warm welcome to all the faculty members of NIT Calicut and especially to the colleagues from, as in any program, the pillar of any program is its participants, and I welcome all the registered and other non-registered participants, those who have shown interest in this program. I also welcome our PhD students, MSc students, and as well as students from the other departments of NITC and also our alumni of Department of Chemistry and NITC to this program. And we have received an overwhelming response from the students all over India. Participants from IISc, IITs, and universities and other institutes have registered for this program. And there was a request from one of the ICs that the content of the workshop should be streamed on online on YouTube, and we have made arrangements for that also. And we have for this workshop, we have eminent speakers from India and abroad. And also we have live demonstrations, and also we have technical sessions from the industry, experts from different industry experts from Agilent Technologies and Argent Life Sciences also. I hope all the students will get benefited by this program. And with this, I conclude my words. Anjita?
Thank you, sir, for the welcome address. Now it's my honor to invite Dr. A. Sujit, Head of the Department, to brief about the Department of Chemistry. Please, sir.
Sujit, sir, your mic is muted, sir.
Sorry. A very good morning, all of you. Respected director, coordinators, and faculties, NIT Calicut, my dear students and participants. First of all, I would like to congratulate Dr. Anuj Varghese and Dr. Lakshmi C. For arranging a very wonderful platform for discussing about nuclear magnetic resonance spectroscopy and other techniques for the measurements. And I knew that there is a large number of participants. They got a very good some details about National Institute of Technology Calicut and also regarding our institute. NIT Calicut is situated 22 kilometers northeast of Kozhikode, a city in North Kerala. And it was established in 1961 as a regional engineering college and was upgraded and renamed in 2002 as National Institute of Technology Calicut. It is a matter of pride that our institute is celebrating its Diamond Jubilee year in this year. The creation and dissemination of knowledge through research is one of the core functions of higher education institutions. Our institution has been providing a wide spectrum of services to society through the vibrant culture of research and academics. The 120 hectares campus provides a repellent atmosphere to academic and extracurricular activities with ample greenery all around. I would like to inform you that our institute is actually in top rank in the category of institutes of national importance, central universities and CFTIs in the Atal ranking of institutions of innovation achievements by MHRD. and NIR ranking of 25 in 2021. Regarding the Department of Chemistry, it is established in the same year, 1960, an integral part of Regional Engineering College, Calicut. In education and research, the department is emerging as a major center of excellence, even at the international level. The academic activities of the department are supported by highly qualified and experienced faculties who pursued research in the frontier areas of science. The major research areas covered by the department include theoretical and computational chemistry, polymer science and technology, organic chemistry, coordination chemistry, physical chemistry, bioorganic, bioinorganic, and medicinal chemistry. The department is well equipped with state-of-the-art instrumentation and other laboratory facilities. Currently, 47 research scholars are working in the department. When we look to the last 5 years, 26 PhDs are awarded from the department. Out of these, 21 were placed in academics and industry. Other students are doing their postdoctoral fellowships in India and abroad. And also in the case of PG students, around 50% were placed in industries, and the other 50% got the opportunity to pursue PhD. The research activities in the department are generously supported by the external, national, and international funding agencies. Also, department has undertaken about 10 crore sponsored research projects. And this is the department that produced highest number of research papers and patents in the institute itself. The department also has collaborative research programs with the national and international universities. And we believe that the excellence is a journey, but not a destination. And the department has diligently set forth a vision of high quality performance in chemical education and training. So with these words, I am completing my speech. All the best wishes for the program. I request all of you, especially the students and participants, to make use of this platform. This is a very wonderful platform. Thank you. Thank you very much.
Thank you, sir. Now it's time for the inaugural address. It gives me immense pleasure to invite a respected director in charge, Professor P.S. Sati Devi, who constantly extends love and support to the departmental activities. Professor P.S. Sati Devi is basically an electronic engineer and a member of Institute of Electrical and Electronics Engineers. With great honor, I welcome you, madam. Please, ma'am.
Dr. Sujit, Head of the Department of Chemistry, Dr. Anuj J. Varghese and Dr. Lakshmi C., coordinators of this online workshop, other faculty colleagues, staff, students, alumni, and most importantly, the participants of this program. A warm good morning to you all. It is indeed a great pleasure for me to inaugurate this CERB Accelerate Began sponsored online workshop on methods of data acquisition and analysis in NMR and HRMS and organized by the Department of Chemistry, NIT Calicut. I sincerely appreciate and congratulate the coordinators, Dr. Anuj and Dr. Lakshmi, for organizing this workshop, that too during this pandemic time. As you know, the objective of this workshop is to train the participants on the applications of NMR and HRMS techniques for their research in order to IT. I'm very happy to see that from the coordinator, I could know that we received a very good response from different parts of the country. So that itself shows how significant this workshop is. And this workshop is being hosted as a part of our Institute's Diamond Jubilee celebrations, as mentioned by our head of the department. I am very proud to say that even during this pandemic situation, okay, which we have been facing for the past 1.5 years, our institute has been organizing various technical as well as non-technical events such as international conferences, faculty development programs, short-term courses, webinars, workshops, training programs, etc. And as Dr. Sujit mentioned, Department of Chemistry is actively involved in cutting-edge research to problems. Most of the faculty have funded projects around, say, as he mentioned, of rupees 10 crore. Most of them publish research papers in high-quality journals. Few of them have patents also. And all faculty are highly dedicated and globally competent. Most of them have research collaborations with the higher engineering technical institutions in India as well as abroad. I take this opportunity to congratulate Department of Chemistry and especially the coordinators, Dr. Anuj and Dr. Lakshmi, for conducting such a workshop, which is highly significant. From the brochure, I can see that this workshop will mainly focus on NMR methods for structure elucidation, NMR spectroscopic analysis of peptide structures, applications of NMR chemical shifts towards characterizing DNA G quadruplexes, development of NMR methodologies for the investigation of weak molecular interactions, biomolecular NMR in solution and solid state, NMR instrumentation, solid state NMR instrumentation, HRMS and its pharmaceutical applications, variable high pressure NMR of proteins, NMR data analysis, etc., etc. So, as you all know, this nuclear magnetic resonance and high resolution mass spectrometry are two inevitable tools for researchers who develop new materials and work in the frontier areas of science and technology. Recently, under the Higher Educational Finance Agency scheme, FR scheme, a 500 megahertz solid state NMR instrument was installed at the institute, and an HRMS instrument is already sanctioned under the DST FIST to the Department of Chemistry. As I mentioned earlier, this workshop is intended to train the research scholars as well as PG students on the application of these techniques for their research and, say, PG projects. Hence, I request all the participants to actively and seriously attend all sessions, take part in all the discussions, hands-on training or the live demonstrations by the various industries, and the training during the next 7 days of this program. I'm sure that all of you will be highly benefited from this workshop. Once again, I congratulate the coordinators and the Department of Chemistry for organizing this workshop. And also, they were very keen in selecting excellent resource persons from reputed institutions, R&D organizations, and industries for handling the various technical sessions. I officially declare that this workshop is being inaugurated, and I wish all success for this program and wish all the participants a happy and wonderful learning experience in the coming 7 days. Thank you. Thank you all.
Thank you, ma'am. It is grateful to hear you. I express my gratitude for your kind words on behalf of Department of Chemistry. Now, I cordially invite Professor Lakshmi C, Workshop Coordinator, to deliver a word of thanks. Please, ma'am.
Thank you, Anchita. Very good morning to our chief guest, Professor Sadi Devi, Director, NIT Calicut, Dr. Sujit, HOD Chemistry Department, all the participants, my dear colleagues and students. it's my privilege to propose a vote of thanks and acknowledge the contribution of all those who work really hard to make this event happen. Professor Sadi Devi, who spared her time from her busy schedule to grace the occasion. Her constant support and encouragement have always been an inspiration to us. Thank you very much, ma'am.
Thank you.
We are also grateful to Dr. Sujit, HOD Chemistry Department, for supporting us wholeheartedly. All the help you provided is highly appreciated. We thank all the resource persons. Participants are going to benefit highly from these expert lectures. Thank you very much for joining us. Dear faculty colleagues, please accept our sincere thanks for the excellent support you provided in organizing this event. I also thank the non for their help during the various stages of organizing this program. We thank all the participants for registering for this workshop. We earnestly hope that this one-week workshop on NMR and HRMS would enhance your knowledge on these two inevitable analytical techniques. Thank you once again for joining us. And my dear students, without your support, we would not be able to organize this event. You guys are great and your contribution is priceless. Thank you very much. And finally, we would like to thank SERB for financially funding this event under the Accelerate Begin program. So we wish you a very fruitful week ahead. Thank you very much. Anshita?
For the delay, ma'am, network issues. Thank you, ma'am.
You couldn't hear me?
Yes, ma'am. Now I can
Okay.
hear you. There was a delay, network, some problems. Sorry, ma'am. With this, we can wind up the inaugural session. Many informative sessions are scheduled as part of the workshop. Please do utilize and imbibe the new arenas of each and every sessions by Rion speakers. We expect your active participation throughout the program. The first session will start at 11:30 a.m. Kindly be online on time. Thank you. Have a great day.
Hello, sir.
Hi,
Good morning, sir.
morning.
Okay.
I have to quit and reopen because I think the screen sharing requires me to change some system preferences.
Sir, you're using a Mac?
I'm using a Macintosh.
Yeah, sir. Then, sir, actually, yeah, you have to quit it and rejoin. Yes, sir. Right, sir. Yes, sir.
I just
We are
changed
waiting.
my preferences, but for some reason it doesn't seem to be using my desktop app. I do have WebEx, but
Okay,
for
sir.
some reason it is using the
Web-based version.
browser. Yeah. Anyway, let me just quit and
Quit it and
reopen.
yes, sir. We are waiting, sir. Okay. Yes, sir. It's visible.
Yep.
Professor Narayanan, good morning.
Good morning. Good morning. Sorry, I was muted.
Yeah, I'm Professor Unnikrishnan.
Ah.
I'm here to assist you for this session.
Okay. Thank you very much. Thank you.
I think you are in office.
Yes. I am in my office. Yes.
And IIT Delhi is fully operative now, or
Well, it depends on what you define fully. But most of us, at least the faculty members, are here. Our teaching is still online. But I think when I last talked to somebody in a position of responsibility, about 20% of the students were here. That's what it was maybe a week or two ago.
Okay.
But I hear that there is a move to bring most students back to campus. When that would happen, I don't know. Yeah, but we're having 20% of students on campus. But classes are still online. Anyway, I mean, this is our exam week, so.
Yeah. Okay. Sessions that could be last time we know you brought in some students from session.
I didn't hear you. I didn't. Come again, please. Could you come again, please? I could not hear you very well.
Narayanan sir, am I audible now?
Absolutely, yes.
Perfect. You are also audible, sir. Thank you.
Good morning.
Good morning, dear delegates. Welcome back to the 7-day online workshop on methods of data acquisition and analysis in NMR and HRMS, sponsored by DST SERV under Accelerate Vigyan scheme. Now we are assuming to the technical sessions. We kindly invite your active participation. Our first honorable speaker is Professor Narayanan D. Kuru from IIT Delhi. He is going to give us a lecture on the topic Understanding NMR Methods for Structure Elucidation. I humbly invite Dr. Unnikrishnan, Professor, NIT Calicut, to chair the session. Sir, please.
Thank you very much. So kind of you for the introduction. We are truly privileged to organize an online workshop entitled Methods of Data Acquisition and Analysis in NMR and HRMS. So a big word of appreciation to Dr. Anuj Verghese and Dr. Lakshmi. We have an eminent professor from IIT Delhi today with us for the first session. He is Professor Narayanan D. He is a well-known NMR specialist within our country and outside the country, a man having extensive international exposure. NMR methodology is his true field of specialty. He had his PhD in 1992 from California Institute of Technology. Subsequently, he moved to Switzerland, University of Lausanne, for his postdoctoral assignment for 2 years. Then he joined as a research associate at Sweden Stockholm University. And in 1997, he joined the IIT Delhi Department of Chemistry as a faculty member. And he could build up a very strong research group. You might have seen, I'm sure you have, many of you have seen his research articles in Journal of Magnetic Resonance, etc. His primary focus of research currently includes adiabatic pulses in NMR, cross-correlated relaxation, and heteronuclear decoupling in solids. So we have to add so many things to his credentials. You can visit the website of IIT Delhi to know more about Professor Narayan.
Pune sir, you are not audible.
Yes, sir. Yes, sir.
So, with this briefing, I'm extremely glad to invite Dr. Narayan to this program for chemistry.
Thanks to the video, I imagine now it is my turn to talk. First of all, I would like to thank the organizers, Professor Anuj Varghese and Professor Lakshmi, for having given me this opportunity to talk at this workshop, and giving the first technical lecture is a big ask. I also noticed that some of my friends and colleagues were eminent, like Professor Raghuttama, Professor Surya Prakash, Professor Vijayan, etc. are here, and could be just as well that one of them could have done this instead of me. So in any case, since I gave this as a possible time, I guess I got this opportunity. Now, with that said, and I noticed that it has some fantastic speakers. So I wish all the best to all the participants. I think you're going to learn a fair amount. All right, so this is, so I'll just get started right away. What I'll do is talk a little bit about some of the techniques. I understand that it is mainly designed for MSc and PhD students or something like that who are studying. So this is quite a very basic talk. And what I will do is not just show PowerPoint, which I don't use, by the way, but I will scribble on this as I go along if I need to. So that's the title of my talk, and in case anybody is interested, you could always email me at any point at this address. So you just, that's my address, and that's the best mode of communication, I noticed. So what I'll talk to you about is a quick introduction to NMR, and then the kinds of structural parameters that I that one can extract out of 1D NMR. And then I'll talk a little bit, depending upon the time, about multidimensional NMR. So I noticed that, like I said, Professor Raghuvattama, Professor Suryaprakash, and Professor Vijayan are here, and they are experts at structural elucidation much more than I am. So they'll probably be talking about other things, even more fancier than what I talk about. I'll keep it very, very elementary, my discussion. And what I will also say, how is it that okay. What I would say is that if you have any questions, you either type it up in the chat box. I don't want it to be a one-way thing. It doesn't matter how much I end up discussing, but it's good to just get some discussion going. That's more important than delivering a lot of material. I don't have that much material anyway. So with that, so if there are questions, you can type it up on the chat box, and somebody could relay it to me. I find it very difficult to pay attention to the chat box and a lot of other things. So with that, we'll get started. So this is, I'll start by a quote from, and it's probably inappropriate in this workshop because everybody knows what NMR is about. But I couldn't resist. This is taken from a very famous book these days by Malcolm Levitt, and it says that the reason, and you can read this also, and maybe I'll show this quotation at the end of the presentation as well. Richard Ernst says it's NMR, at least for some of us, it's a playground where you can do a little bit of fundamental physics or chemistry. But finally, the reason is that the applications that NMR has is what drives all this. And this is along the same vein that, as NMR has diverse applications. But what I will focus on is what mainly structural chemists, because I work in a department which is mainly structural and synthetic chemistry, and as a result of it, I realized that the majority, at least, of the users that I come across, and it's probably of many chemists, is that people are interested in identifying structures of small molecules that they synthesize. So my whole talk revolves around that. I'm sure that people like Raghuvattama, Suryaprakash, and Vinesh will talk about bigger molecules and more complicated sequences, etc. Okay, so with that, we will go into an introduction to NMR. And I do this at every talk. I have to first lay the groundwork. And NMR is a form of spectroscopy. And so from the time of Kirchhoff or Bunsen or whoever it is, the idea of spectroscopy is very straightforward. You get light, electromagnetic radiation of whatever particular frequency, and you put this, it impinges on a sample, and either the light that comes out, you disperse it on a spectrum using a prism or whatever. That's what Newton did. You disperse it, and then you look at this. That's the idea of spectroscopy, and it is the interaction of electromagnetic radiation with matter. And typically, in spectroscopy, that at least that we encounter in other forms of the electromagnetic radiation, there are two processes that typically occur. That is, one is absorption, where if you thought all these things are quantum mechanical. So the basis of all this is that it is quantum mechanics. So if you have molecules in the ground level, it's a quantum mechanical state. When you shine light, it gets excited, and that's the absorption process. Yeah, that's one thing that could happen. The other thing is, this is typically what you would see in ultra. And the other thing that happens is, as in fluorescence, time resolved fluorescence, for example, the molecule goes up into the excited state, as it is here, It comes back down to the ground state. It emits radiation. So that's the emission process. The reason I say this, and I spend so much time on this, is because NMR spectroscopy does not fit this paradigm. It's a common mistake, and I'll come to that in a moment. So this is something that one of the things that I like to stress on is that NMR does not fit this normal recipe for spectroscopy that we encounter. And this is the form of spectroscopy, even for NMR, that most teachers teach students. But unfortunately, this idea is incorrect. But the thing to note is that NMR lies at the, if you have, this is the electromagnetic spectrum with the frequency increasing this way, that is energy increasing this way, the NMR is in this area. And what I tell people is always think of it in terms of your radio stations on your whatever mobile telephone, let's say. Think of it in terms of radio station. And that's the way to think about it. So typically the radio stations will have something like 100 or so megahertz, so something around 90 megahertz. We are somewhere around that, 90 to 110. If you're looking at frequency modulation, it's about 90 to 110 megahertz. NMR is similar. It will typically start these days maybe at about 300 or 400 megahertz, although there are tabletop instruments which run at around 60 or 80 or 90 megahertz. So they'll typically start at 400 megahertz. And if you talk to the people at ISC Bangalore, like Raghotama, Suryaprakash, or at ISA Thiruvananthapuram, people are talking about 800, 900, 1 gigahertz, something like that. But it is, you think of it, it is like a radio station. So that's something that to get an analogy, always think of it in terms of radio stations. That's important because 106.4 FM gold will be different from, at least in Delhi, FM 107.2 is radio nasha. Nasha means intoxication. So yeah, but this is important to get it into your head that it's like radio stations, okay? And often, typically, at least I must admit that when I finished my MSc, I had barely seen an NMR spectrometer. So for many of us, at least from India, you might not encounter an NMR spectrometer until you get your PhD. So that's the typical look of it. It might vary a little bit here and there. There is a big ugly object here, which is a magnet. That's a supercon magnet. That's like the heart, very important. Without that, nothing is going to work. And like everything else, including your mobile telephone, there will be a computer. So that's, every spectrometer has this, UV visible, whatever. So there's this computer here. And then this is just RF electronics. Okay, so this is a box. You call it a console, people will call it. And to give you an idea, again, I'm not an expert at this because I don't buy so many spectrometers. But if you looked at it, a 400 megahertz spectrometer, just to get you a sense of, will cost you about 3 crores. Let's say. 3 crores, huh? Not 1 or 2, 3 crores. And inside this magnet sits a sample which looks like this. Okay, at least for liquid state, let's call it. So it's a glass of silica tube in which there is sample at the bottom, and this sample at the bottom sits in here. It's a core. And it just sits there. That's what it is. And this red object is called the valve, something like the probe. And here is what you apply. You do all your the action all happens here inside this magnet. And the magnetic field is what typically about 10 Tesla, 15 Tesla, 20 Tesla, something of the order. It's quite, I mean, if you walked in there with a credit card, you can be sure that you'll have nothing of it at the end. So it's quite intense magnetic field. And if you want to just get your attention as to what it is inside this is the magnet we talked about, which I've represented as NNS. And around this is your sample here inside. So this sits into your magnetic field. And this is a coil. Think of it, don't think of it, this is called Helmholtz coil, but doesn't matter. Think of it as a solenoid. Think of it as a solenoid. A solenoid generates a magnetic field, and that is at a particular frequency. So you have you're putting an electromagnetic radiation of radio frequency, which is generated by a synthesizer. What is the synthesizer? Again, think of it as a radio station. So when you dial the dial to 106.4, which by the way, I seem to like 106.4 FM Gold. I think that's an AIR station and exists across the country. So if I turn my dial to 106.4, this frequency synthesizer will put out radiation at 106.4 megahertz. So at the computer, I sit down and I dial 106.4 or something like that, or 400 megahertz. The synthesizer puts out electromagnetic radiation at that frequency. And then it's a gate, and attenuator is nothing but a gate that we have at home. It opens and closes to let this radiation go in. Attenuator, we know, is just, you decrease or increase the intensity of the radiation that comes in, and you amplify it and put it to the sample. And this is where it's different from other forms of spectroscopy. You apply the radiation and then you remove it, the same as in fluorescence. In time resolved fluorescence also, you do the same thing. You apply, let's say, ultraviolet or visible radiation. The molecule goes up into the excited state and then it decays. Except that is spontaneous emission. In fluorescence, there is spontaneous emission. So the same thing happens here. You excite, well, don't call it excite. I don't like to call it excite. You do something, and then you remove this radiation, not like UV visible. You remove the radiation. And when you remove this radiation, the sample comes back to equilibrium. And while it comes back to equilibrium, you detect the signal. This is another amplifier, except that it is low noise, high gain, and it will make sure that it takes the signal, which is very small, and then does something on the computer. So that's the overall idea. So just if you prefer to think of it in terms of what happens experimentally, that's what, because people are all of different types. Okay, so now we come to what it is, how we do this, what this happens when we do this. So a nucleus, let's say proton, some nuclei have a spin. That's an intrinsic angular momentum. So this is an intrinsic angular momentum. It's like the electron. The electron also has a spin. So this has intrinsic angular momentum. Where it comes about? Well, not something that we will worry about. Let the physicists worry about where it comes from. We can argue about it if you wish, but let's not worry about it. So it has intrinsic angular momentum, which means that some nuclei, no matter what you do, by default, are spinning about its axis. Okay? And when you have, so it's spinning about its axis, when you have something which looks like this, it generates a magnetic moment. This is all high school physics that you and I have learned. Nothing very complicated. When you have a spinning object, spin angular momentum, it has a magnetic moment, which means that these nuclei behave like bar magnets. So nuclei behave like bar magnets. More or less, you can think of it like that. So they behave like bar magnets, except that the bar magnet is not spinning about its axis. That's the only difference. But otherwise, it looks like a bar magnet. Not all nuclei have this intrinsic spin angular momentum. This is given by I. The intrinsic angular momentum is given by I. So some nuclei have an intrinsic spin angular momentum. Electron has a spin angular momentum, which we call S. Some nuclei have it. People will say that charged objects would have a magnetic moment because if they're spinning, it will create. But if that is the case, then you can't explain that the neutron, which is not a charged object, also has a spin. So the neutron has a spin of a half too. Proton does have a spin of a half. So proton, electron, etc., you will say these are charged objects. So when you get this magnetic moment. But it's true of neutron as well, which is an uncharged object. So this has, so it's something, it is intrinsic. That's the easiest way to think about it. If you wanted to do the physics, then you'll have to look at some nuclear physics. But anyway, it's very low energy. So when you take this bar magnet and you put it into a magnetic field, typically what happens is that a magnetic field is there. This magnetic, if you put a bar magnet, it will tend to align with the field. It will tend to align with the field. That's if a bar magnet is there, but this thing is spinning about its axis. So this thing, the spin, so this is like exactly like what happens with the Earth. The Earth is spinning about its axis, and the Earth itself is rotating about the Sun. So that's exactly the same thing that's happening. So this nucleus, which is this bar magnet, spins about its axis, and this magnetic field is trying to pull this here. So what happens is this thing will execute a motion around this, which goes on forever, and this motion is called precessional motion. Okay. In quantum mechanical terms, if you thought about it, if you have a proton, let's say, which has a spin of a half, we'll say that there are two possible values that the spin angular momentum can take with respect to the z-axis. So the z component of the spin angular momentum could have two possible values those are the two possible states. One is plus half and the other is minus half. The plus half states corresponds to where this north-south is, well, so-called aligned with the field, and there's one which is where it is opposed to the field. So these are two possible values of the z component of the nuclear spin angular momentum. If you took an electron and put it into a field, it's the same thing that happens. Okay, and if you did this now, and if you took an ensemble of spins, which is, let's say, imagine an Avogadro number of spins, then you will get a Boltzmann distribution. But before we go to that, what is important as chemists is that a large number of nuclei, have a nuclear spin, and this I have just listed, and this is something that chemists typically worry about. We are looking at spin half, whereas if you were an inorganic chemist, then you probably are going to look at other nuclei which have spin greater than half. So if you looked at this, you find that for us that this is of great importance. If you were doing, small molecule structural elucidation, proton is very important. 13C is also has a spin of a half. If you were looking at biomolecules, P31 is also a spin of a half. So, and then F19, if you were looking at drugs, for example, where there are a lot of fluorinated compounds, F19 is another possibility. But you will notice something very interesting is that the 12C, which is, if you were an organic chemist, 12C, which has a natural abundance of around 99%, has a spin of a 0. And that's because the mass number, if the mass number is even and the atomic number is even, then the spin is 0. So 12C happens to have no nuclear spin. And this is very, very important, crucial for structural elucidation of small molecules. It's a blessing in disguise in some sense, but it also could be a difficulty in some other sense. So for most small molecule organic chemists, that carbon 12 has no nuclear spin is a blessing in disguise. Okay, so we are looking at, in our case, only looking at spins which have a half, and we'll focus our attention mainly on proton and C13. Remember that this has a natural abundance of about 1%, a little over 1%. So if you took 100 molecules on all, then you'll find that 99 molecules would have C12 and only one molecule would have C13. So out of 100 molecules, you have 99 12CH3OH and one molecule will 13CH3OH. So only that one molecule is going to give you signal. The other one doesn't. Okay, and now this is critical. NMR is not like other forms of spectroscopy. And this is key to understand this, because all of NMR nowadays developed is based on this idea of how we do spectroscopy in the radio frequency regime. So we said when you have a spin of a half, we said that the molecule, the nucleus can either have its Z component be plus half or minus half. So there are two possible states, one which is lower and another which is higher. So this is when you apply a magnetic field with energy increasing this way. So there's one state which is plus half and another state which is minus a half. And we know we appeal to Boltzmann. So if you, this is at some temperature, room temperature, let's imagine, what Boltzmann would tell us is that there will be a small excess population in the ground state as opposed to excited state. And this population difference, which I have represented by 4 dots here and 3 dots here, this difference is proportional to the temperature and this frequency separation or this energy separation. So it's proportional, it's related, not proportional, it's related to the temperature through the Boltzmann distribution. So as the energy increases, then this Boltzmann distribution, the separation or the difference in population between the ground and excited state increases. And we know from spectroscopy, the sensitivity or the signal to noise or whatever spectroscopists would call will be proportional to this difference in energy, because the population increases as the separation increases. And we know that if you looked at it from a quantum mechanical standpoint, this separation here will correspond to the same frequency at which that nucleus was going around the magnetic field. So this separation is given by, well, ideally this should be a negative here. So omega naught is equal to minus gamma v, okay? It's not plus gamma v. So what happens as a result of this is that if you have an Avogadro number of spins, you have a large number of spins which are all going around like this, and you will find that along the field there will be a marginal excess, right? So if you take this Boltzmann, what we are saying is, if we have 10,000 spins, you'll have, or 2 times 10,000 spins, you'll have 10,000 spins plus 1 in this direction and 10,000 spins in this direction, right? So you have 10,000 plus 1, 10 to the 5 plus 1. If you took 10 to the 20, then it will be different. But if you have 10 to the 5, you'll have 10 to the 5 plus 1 here and 10 to the 5. So very small difference in population between these. Now, if you look at the projection of each of these vectors along this axis, will add up, and that along the xy direction will cancel out, right? Is that easy to understand? So let's imagine that I have a vector here which is oriented like this with respect to the z-axis. That's my z-axis where I've applied the magnetic field. If I have a vector here, this is one of the vectors here. This is the projection along the z-axis, and this is the projection along the xy axis. And you'll notice that because vectors are all around this cone, this will add up and this will cancel out. So along the xy plane, there will be a cancellation and there will be an addition along this. The addition will happen in the negative z direction too, but since I have larger number here, I will have a small macroscopic nuclear magnetization in this direction. Nothing very complicated. It's exactly the same thing that happens when you take a paramagnetic compound and put it into a magnetic field. So if you're worried about it, nothing to worry about. You think of it exactly like what happens in a Faraday balance. Now if you are a starting chemist, then you would have studied that when I take a paramagnetic, so same thing that is typically done is people will say that, look, the Bohr magneton was this many Bohr magnetons, how many unpaired electrons were there? That's exactly, and you do this by a Faraday balance or GUI balance measurement. So if you put a paramagnetic sample into a magnetic field, exactly the same thing that happens. There is a new electron magnetization that is filled up. Here it is 3 orders of magnitude smaller. So this is nuclear magnetization. So finally, what have I got? When I take this sample and I put it into a magnetic field, I have bulk macroscopic nuclear magnetization in this direction. Now what do I do? And this is where it's critical. Now you've got to figure this out. I have a solenoid which is perpendicular to this. This solenoid is the one that I said, radio frequency. So I turn my radio frequency to FM gold. So 106.4. I switch on FM gold and I switch it off. And when the frequency of this matches with the frequency at which this is going around, what happens is, so we know Faraday's law, Faraday will say that, look, if I have a magnetic field like this and I have a magnetic moment or magnetization like this, a torque is generated. A torque is generated which will flip this thing along this direction. That's what we do in NMR. So we apply a short burst of high intensity RF radiation at exactly the same frequency at which it goes, more or less. At least for you, let's think of it as at the same frequency. And what it does is to take your thing and it rotates it. So it has rotated. If you rotate it by 90 degrees, it'll go from, so you started here, I rotated it 90 degrees, it came here, and that's where at that point, I remove the radiation. So at that point, I switch off this. So I switch off the radio, and now what happens is, this magnetization, the magnetic field is still there along this direction. So this will now start, now there is magnetization is like this, the magnetic field is like this, so this will start to go around like this, right? Because it is perpendicular. So the magnetic field is here, your magnetization is reached here, so it will start to rotate about this. And when it rotates, again, Faraday's law would tell you that if I have a solenoid and if I have a rotating magnetization, it will induce a voltage. And what you do is to measure this voltage. So you measure a voltage arising as a result of this magnetization going around like this. And this is very important. Get it here, and this is different from. Now, typically people will say that, look, I have a ground state, excited state. When the frequency matches resonance, they will say one molecule goes from the ground state to the excited state. This is not how NMR happens. Get this right. So I will make this in red. This is not how it happens. If there's anything that I wish that you learn from my talk, is that this is not how NMR happens. NMR happens by this form, and we generate a voltage. Okay, so we generate a voltage, we measure the voltage as a function of time. Look at this. Now, it's very important to understand this. We are measuring voltage as a function of time. A spectrum is what? You have intensity as a function of frequency. A spectrum is this. You have signal as a function of frequency. What I've measured V as a function of T. It's not a spectrum yet. And the question we ask ourselves is, how do I go from voltage as a function of time to spectrum as a function of frequency? That's the next order of business. Now, how do I go from something which looks like this to something which looks like that? Okay, and this whole thing of how I do this is represented in a musical score. So this is where the pulse comes. So I represent it in this fashion. So this is where the pulse comes, and then I measure the signal. So if you look at any paper these days which talk of NMR, they will draw sequences like this, and it will look incredibly complicated, but it's all very straightforward. So you will see these bars like this. Sometimes they'll be dark, sometimes they'll be double the length, sometimes they'll be 3 times the length, but whatever it is, you'll have a bar like this followed at the end by something which looks like this. So this is the signal that we detect. We measure a signal as a function of time, and we want to get, for the spectrum, we have to go from signal as a function of time to signal as a function of frequency. So now that's the next order of business, to go from signal as a function of time to signal as a function of frequency. And it's a very, very straightforward thing. Well, in the 1960s, it was a big deal, but now any computer would have it. What you do is, so you've measured this. So this is your signal as a function of time. And what I do is I multiply this with something which is an oscillating frequency. Let's call it minus I omega t. I multiply it by this. So if I take this and I multiply it by this is what I get. Okay, I get, if I take this product, this is what I get, and you measure the integral, which means the area under the curve. So, and you can think of it, I mean, you'll say, oh, how did I get it to be 0? That you can see. Every time I have a positive deviation, I have more or less a negative deviation. So if I looked at the area, every positive area is cancelled by the negative area, and you will get an integral close to 0. Doesn't matter if it's exactly 0, but you'll get something which is close to 0. So I have guessed a function. This is my guess function. This is what I measure. So this is a measurement. I'm trying to do this pictorially. This is a measurement. This is my guess. And I take the product and then I find its integral and I find it to be 0. Now, notice what happens when my guess matches this frequency. When my guess matches this frequency, this thing here is what the product is. And look at this. There are no negative deviations. So if you look at it, the area under the curve is different from 0. And this is all there is to Fourier transform. So this is what a Fourier transform. And then whatever result I get, I integrate. And if you did this, this is what. So this is what the whole thing about Fourier transform. So here's my signal. I do a Fourier transform. So when my guess is good, I'll be here. That's my integral. And when my guess is bad, whether it is slow or fast, I'll be here. So, and when the guess is good, I'll be here. And this is now, so if I can do this on a computer, then I can get my signal as a function of time to signal as a function of omega. This is signal as a function of omega. And this is what we do on the computer. And once we do this, you have your spectrum. So this is the mathematics, one of 3 equations. So this is my signal. This is my frequency at which it's oscillating. And this is the width. Let's not worry about this. If your teacher is talking about it, your teacher would say that this is what is called the spin-spin relaxation time. Don't worry about it. It's nothing. It's something which just makes the signal go to 0. Right? This is, you have perturbed it and your magnetization is going back to equilibrium. So after a perturbation, then this has to go back to normal, right? And if you want to give a Kerala analogy, if you drink a lot of alcohol, and alcohol is very popular in Kerala, I know this because I also happen to be from Kerala. So if you drink this, by the morning, that nasha has gone. So that's what is happening. So this is exactly like the nucleus is doing exactly the same. So the pulse comes and it decays as a function of time, and I measure this. For some people, it goes away in 2 hours. For some people, it takes 4 hours. So this is a measure. And I take this, multiply this, and integral. So this is the mathematics of it. Very simple, but the important thing is I can do it on a computer like that. Before you give me, I'll give you this what it looks like. Okay, so that's the underlying thing. The take-home message is NMR is not like other forms of spectroscopy. That's very important for you to understand that. Maybe this is a good point to take a short break. And if you have any questions, then I'll be happy to answer them now. The second part is talking about some of the techniques that one uses. If there are any questions, if not, we'll move on. I can't see anything else on my screen. I only see my own screen. So,
please, audience, please, if you have some queries in between, this is the ideal time to float it. Please, you can speak to us, or you can type at the chat box, please. We wait for your queries, please.
I might end up discussing lesser than what I planned, but that doesn't matter. It's not important. Okay. Are there any
queries, please?
It's okay. People are just waiting up. So first session.
Please, we'll continue, sir. We'll continue.
Okay. All right. So let's move on. So now this is as far as what the technique is. So now we'll go into what is it as a chemist? I'm a chemist. So if this is all there is to it, it's a waste. So the first thing that we have to know is that you can use this, and this is a very nice quote from Niels Bohr, who says that how NMR works. You know, the nuclear spins act as spies, he says, right? So they give us, relay us information about the molecular structure. So that's what he's talking about. So we don't put little spies. Spies are there naturally, and we just probe them. So we give some information. The radio signals is what we give to the spice, that is the nuclear spins, and they relay us back structural information. So that's a good way of thinking about it. So the first thing that we know, and all of this is the stuff that you know. I mean, if you have reached MSc, then this is stuff that you know. It's just that I'm giving it a simpler, well, I don't know if it's a simple explanation, but I did not get the simple. Can NMR signal be, oh geez, it went away. What is the question? Let me see. Give me a second. Let me see what that. Can NMR signal be manipulated? Okay, it can be. Well, okay, the question is from Shivangani. Is that the name? I missed the name. Yeah, Shivangani Pundir. And the question she asks is, can NMR signals be manipulated and how? NMR signals can be manipulated in some sense, in the sense that I have control over what I do, right? These pulses that I showed you here. There are two things. I skipped a lot of the underlying stuff. So if you talk about it, this is answering the question of Shivangini. See, there are three things that are in our control. One is the length. That's one thing that I have in my control. 3 or 4. Then this is in my control, the amplitude. So the height of this, and these are linked in some sense. So this is the amplitude is in my control. And there's also a phase, something which we call the phase, which means that, and this is why NMR is different from other forms of spectroscopy. If you look at in the rotating frame, I can, and as this thing rotates, I can apply it in different directions. So that's one thing. And then if I do more than one pulse, then I have also the timing, right? So if this is one experiment. So now this is very important to remember. So I apply a pulse, and then I detect the signal, and then I wait for the system to come back to equilibrium, right? So think about, this is something to understand. This is different from UV visible form of spectroscopy. So it comes back to 0. Here there is no signal, means that signal that, well, more or less the nuclear spins have come back to equilibrium. Then I will repeat this experiment again. So what I will do is I will repeat this again. I'll apply the same thing again. And then I'll measure the signal again. And this signal I will add to this. I will add the 2 signal. And then I'll repeat it 3rd time, 4th time, 5th time. Because you notice that radio frequency, the separation is small. So very little signal. In UV visible, you can do with very little. If you're doing mass spectrometry, which is your second half of this course, you need only femtogram. In NMR, you need a lot of sample, because we are looking at, energy separation, which is small. So we have to repeat this. So this process is repeated many times, and this is called signal average. Now that's something which is routine in NMR. So we repeat the experiment many times. So after this thing comes to 0, I then repeat this. I repeat it 100 times. Let's imagine 100, 200,000, whatever. So then yes, yes, it is under control in some sense. I can manipulate, but I can't manipulate how much signal I have, right? This signal that I have is determined by the sample, the magnetic field, etc., etc. How good your probe is, etc. That I have no control over. In that sense, I cannot manipulate. But what I get out of there, that I can manipulate. So that is manipulated. So that's the answer to the question that Shivangini asks. Yeah. Oh my goodness. I ran away. This is a problem. I'm editing a PDF file, so turns out that it's okay. So yeah. So So now this is as far as, this is as far as how NMR works. But if it has to be any useful to chemists, that's not going to be very big deal. I mean, it's a waste. But there's something very interesting that happens. Every compound that I take is made up of, and in addition to nuclei, I also have electrons, right? And electrons are from quantum mechanics are in ceaseless motion. So when they are undergoing ceaseless motion, what happens is they generate, because of this charged object undergoing motion. You can wait for the books, Sachin, till the end of the talk. I'll give you some examples of books that you could read if you wish to. So these are charged objects. So it's undergoing some motion, some rotational motion, let's imagine. So when we know again from high school physics, so if you have a charged object in a magnetic field and it's undergoing rotational motion, it will generate a magnetic field. So the electrons that are there in the molecule, their motion will generate magnetic fields, which I have written by these symbols here. As a result of which, if I have a molecule which looks like this, then different nuclei are at different points here in the molecule. Because of this magnetic field that is generated by the electron motion, the magnetic field at this location is different from the magnetic field at this location. Now you understand? So I have a molecule which has nuclei at fixed positions. I have electrons which are undergoing motion, and the electron motion will generate a magnetic field, which means that nucleus at this point will feel a magnetic field which is different from the magnetic field at that point. The local magnetic field. The outside magnetic field is the same. Remember this. This magnetic field is the same, but the local magnetic field felt by the nuclei are different. If the the nuclei only sense the local magnetic field. So if you took the socially relevant molecule ethanol, for example, if the magnetic field felt by all the nuclei are the same, you would get one line. But because the nuclei at different locations in the molecule, which means that if I'm looking at protons, these protons sense a different magnetic field from this proton, I will get 3 different resonances. If you were doing it in the early days, it used to be like this, but now if you looked at it, it might be something which looks like this. So now this is one information that is of great use for a chemist, because now I can differentiate. You look at this, you can differentiate from the methyl, from the methylene, from the hydroxyl, because the environment is different. And this is one of the biggest reasons for the use of NMR in structural elucidation. And this arises as a result of the local magnetic field that is different. So the electronic environment affects the resonance frequency. So if I took this particular molecule, for example, what happens is the environment here is different from the environment here, is different from the environment here. So you'll get 3 different resonances. So depending upon the type of proton, I will get 3 different resonances. This is a very, very big, although it's very small, it's a very big thing. And this is one of the reasons why, I mean, people tend to forget where this comes from. And this is the reason why NMR is so powerful in chemistry or for any structural elucidation. And it's interesting that chemical shift. So this was called by Felix Bloch, who was a physicist and one of the founders of NMR, a chemical shift, because Dharmati, who was working in his lab, had taken this sample, I think ethanol, and threw it into the NMR spectrometer and saw this different. And Bloch wasn't very excited. Being a physicist, he wasn't very excited, and he said that it must be some chemical thing. But now chemists run away with this. I mean, and this is it's a big, big difference. The other thing that you have to realize is that it's very important to realize this. I mean, I didn't realize this for a long time. It doesn't occur to us. And so we have, let's say, ethanol. If you took ethanol sample, now you can record the carbon-13 as or the proton. So proton, let's call it FM gold. And so if I say that proton is FM gold, that's something like 400 megahertz. It's important to understand these things. Very straightforward, but easily overlooked. So let's say you have proton at 400, 13C will be at 100 megahertz. And the reason for this separation is because the gamma, the magnetogyric ratio, that is the ratio of the spin angular, the magnetic moment to the spin angular momentum is 4 times less for C13 to that of proton. So if you now, I'm recording the C13 and I take a sample of ethanol. This is 98% abundant. Look at this. You have to be careful here. C12, O16, 1H. This is about 98% abundant. Right? Then you have this carbon could be C13, that's 1.1% abundance. This carbon could be C13 and is 1.1% abundance. So this one gives you one signal here, and this one gives you another signal here. They give you two different signals, but both of these come at 100 megahertz. It comes from the same sample of ethanol, but it comes from two different isotopomers. Now realize this, but when you record the spectrum, you will get one spectrum which has both. You will get a single spectrum at 100 megahertz corresponding to two different isotopes. It's very important to realize this. One quickly forgets, and maybe Vinesh or somebody like that who's talking about biomolecules will worry about this. So this is something that you have to get into your head, that they are coming from two different molecules, but the spectrum that you and I see is for the sample of ethanol, comes from two different molecules. So this molecule doesn't talk to this molecule. They are two different isotopes. So you'll get a spectrum which corresponds, and it's a mixture of these two. And this is happening if I turn the radio dial to 100 megahertz. I won't be able to do this at 400 megahertz. Okay, so this is something, and again, people fail to realize. So now let's same thing, the ethanol case. Now I've drawn this. This is at something like what? Some 1500 hertz. This, let's say in hertz, this is about 1500 hertz. And this is around something like minus 1500 or minus 1000 or less than minus 1000 hertz. And so what I'm saying is, on the scale, I will get something which looks like this. I get a spectrum which looks like this. Now, if I recorded the same thing, if I recorded it at 100 megahertz and you recorded at 200 megahertz, this separation in hertz will double. Okay, this will double. So this is, in my case, it will be something like this. If you recorded at 2 times the frequency, you will get double. So if I'm turning it to FM gold and you turn it to 2 times FM gold, this separation would have. So this becomes very difficult to compare. So if you at NIT Calicut, you're sitting there and you're recording the NMR and you send it to me and I'm sitting, I have to compare this becomes difficult. And so the way around it is to just scale it by this factor here. And this factor, this once you are in this scale, then no matter whether you record it or whether I record it, they'll always come at the same frequency. This is in ppm. I again say this because people don't realize what ppm is. ppm is a measure of the frequency. Typically, people get confused that ppm is a measure of concentration. So this is how we do it, and we cheat a little bit because this frequency is so close to omega naught. So we just approximate it like this. And this is important to know. So two frequencies separated by 1 ppm at 100 megahertz will correspond to a separation of 100 hertz. But two frequencies separated by 1 ppm at 400 megahertz will correspond to a 400 hertz separation. So that's something to realize. So in hertz, they will scale with the field, but the delta is independent of them. Okay, and like I said, chemical shift helps in structure elucidation. So if when you, I'm sure I noticed that there are people who are talking about very sophisticated applications of NMR, like quadruplexes, DNA quadruplexes, etc. These are very complicated molecules. The proton chemical shift, which is something that is not listed here, proton chemical shift I missed out, is only about in the range from 0 to 10 or 15. So it's a very small range. But with carbon-13, it has a range of about 0 to 200 pp. And as the atomic mass increases, you will find these ranges increase. So what happens is, and this you have to realize, so if all the protons in a sample come between 0 and 10 ppm, you'll get a very crowded spectrum. This is something that you have to realize. So when you keep this in your mind, the kinds of techniques that Vinesh or what's his name, the guy at Bhopal, I forget his name, whatever. So when he talks of DNA quadruplexes, yeah, so you have to realize this. So they will take proton on one axis, they'll take carbon on another axis. The reason for this is you want to spread it out. Think of it as a classroom where all the students are sitting in the first row, and then you're going to be everybody. Well, no student ever sits in the first row. I never used to sit in my first row either. Yeah, so all of them are sitting in the back row, and then the teacher comes and says, move out. Move out to the front, then everybody spreads out. That's exactly what you're doing. So if you spread things out, then you're crowding. So you will see that this is something to realize. I'm just setting the stage for when the other people talk about it. So yeah, so you'll see that this chemical shift helps in structural elucidation. And I'm going very, very slow. But the other thing that you have, that structural chemists use, is that when you record the NMR spectrum, the area under the curve is proportional to the amount of nuclei that are present. Typically, if you're looking at protons, but not true in terms of carbon. So that's something to realize. Okay, so but again, you'll see that different molecules have spread out. You can see it has something to do with electron density around the nucleus, etc., and you can make these correlations. The other structural information that is very, very important is that when you have, see, each nucleus is a bar magnet we talked about, right? So each nucleus is a bar magnet. And you know from high school that if I have one bar magnet next to another bar magnet, there will be an interaction between these two. These are called dipole-dipole interactions, right? And I'm sure that all of us, well, if you went to lab, then if you have two dipoles like this, you drew the lines of force. I remember we used to do it in high school. So you drew the lines of force and you could see the lines of force. Exactly the same thing happens. If you have two nuclei which are close together in space, there's going to be an interaction. Unfortunately, this interaction through space is something that we don't see in liquid state. But the electrons that are there in the intervening bond. So if I have a nucleus here, and if I have another nucleus here, and there is a bond which there are one or more bonds, then there are electrons here. So the electrons then relay this information between one nucleus and the other nucleus. And as to whether the nucleus are like this, like this, like this, or like this, they'll have different energies. And this is what is called J coupling. And this is very, very small. This is very small energy differences. So this is what I'm talking about. So if I have a nucleus here, which has a spin, and a nucleus here, and there are electrons which are, in the bond which is paired, so they transfer this information from this nucleus to this nucleus, and so the energies are different, and I can measure these small energy differences in the molecule. And that's the other structural information that we have. So this is something that, again, people will talk about 2ni plus 1, etc., etc. So in the absence of a coupling, I'll have two individual lines, and in the presence of a coupling, I'll have this split, and this splitting is the same as this splitting. So I know that then, okay, these two, so the nucleus here is talking to the nucleus here. And as happens in classrooms, for example, well, these days it's different when you have mobile telephones and WhatsApps, but normally in the old days, if you have a student here and your student here, there's unlikely that they will talk to each other. The same thing happens as the distance increases. So you can measure which two. So this is structure, right? If I have a molecule and if I can tell which two nuclei are close together, that gives you an idea about the structure. So that's another information that we get. And you have to realize that this separation that we get in J coupling is independent of the field. So whether you do it at 100 megahertz or 200 megahertz, the splitting that you have, that 12.3 hertz, will be the same irrespective of whether you do it here or here. But if you looked at it in the delta scale, now it will be different, right? Because 12.3 at 100 megahertz will correspond to a smaller delta than when you are doing it at 200 megahertz. So you have to be a careful. And the other thing, and this is something that Vinesh and Raghotama and Suryaprakash exploit, is that the coupling that you have, right? So I'm talking about a coupling here. This is a magnetic dipole. This is a magnetic dipole. And these two dipoles, this coupling is a function of the dihedral angle. You look at this dihedral angle here will determine the coupling. So if I measure, so I can do the reverse if I'm interested in structure. So if I measure the coupling, I know this coupling, then I can tell you, aha, the dihedral angle between these two protons is this. So, and this is structural information. So now I have chemical shift and I have J coupling, both of which carry structural information. And this is what is used. There's a third thing here which people will talk about, and that is something which is called NOE, which will come to that in a moment. But I've only touched the surface. I say that, oh, okay, simple splitting pattern, but when things could get a little bit complicated and you'll get spectra which looks like this. It doesn't have a simple intensity pattern, but one can understand this. Okay, so now we have two things. We've got the chemical shift and we have the J coupling. And as a structural chemist, what we are interested in is to be able to measure these things. Chemical shift is easy enough to measure. You look at the spectrum and you can get the chemical shift. But J coupling is a little bit difficult to measure. So you look at the case of sucrose, and there's a way of measuring this, and this is, so look at the case of sucrose. Sucrose is this molecule here. If you ask me to draw the structure of sucrose, I will fail the test because I don't know what it is. So I had to copy it here. So this is the molecule of sucrose. And you can see that all of these are only in the aliphatic region. So we said in the proton spectrum, it will go from 0 to 10 ppm. And if you have aromatic molecules, then it will be around 7. So, but this is all aliphatic, so it's a very small range. And look at this. This spectrum could get very crowded. So you don't know which is coupled to which. And I have labeled all this. So now there's a very, very interesting experiment which used to be done in the old days, and it is not done now. But you can understand what happens. So imagine that I apply another frequency at this particular point. So this is called a decoupler. So I am removing the coupling. So I do something to the spectrum while recording the spectrum. I irradiate here with a second frequency. This is like saying, if you are looking at the radio station analogy, is I am doing 106.4. At the same time, I am also setting another radio. So think of two radios in the room at two different frequencies, slightly different. This is all in the proton spectrum. So I irradiate this, and you look at this. So if you have, so this is your control spectrum. So look at this range. You see that you have a quartet here. And what have I done? I have irradiated here, and you'll see a change here. So now you know that these two protons are coupled to each other. Okay, this is called decoupling. So I have removed the coupling of G1, and I can see that the coupling is here. But look at how difficult the experiment is. I have to do it at multiple places. So if I decouple here, I see effect on the spectrum here. If I decouple here, I do all sorts of things. So I have to do a lot of things before I'm able to know which two protons are coupled to each other. This is a complicated experiment because first of all, you have to tune two frequencies which are close together. And so that's not an easy experiment, but you can then determine. That's the idea. In the old days, 60s, etc., this is what people used to do. This is called decoupling. The idea is called decoupling, but you can remove this and you can tell which is coupled to. So this tells you which coupling is there. You can measure the coupling, right? So, and the other thing to notice is that carbon-13 spectrum, carbon-13, right? If you have this, let's imagine this is C13, and this signal is the carbon-13 spectrum. This, I believe, is alpha pinene. That's the molecule, some steroid. If you record the spectrum, this is what you get, right? And notice that every carbon is attached. So let's say here you have this is attached to a proton, So each carbon is attached to a proton, so you'll get a doublet. And already the carbon 13 has very low intensity. And if it has very low intensity and it's already low in intensity and you split it in half, you can see that the signal is very low. Forget this for the moment. This is CDCl3. Don't worry about this. But you look at the sample, all the carbons that you're seeing are very, very small in intensity. And now what you do is, and the reason for this is because if you have a proton here, if you have a carbon here, this is coupled to 2 protons and it'll split. So you'll get a triplet. So now what all the couplings to all the protons in one single experiment, then you can get a spectrum which has removed all the proton couplings. So all your C13 spectra are typically recorded in this fashion. Now you notice every carbon has an intensity which is higher than what we started. I cheated a little bit, doesn't matter, but at least certainly I'm getting signals that are higher in intensity. And here is that musical score I talked about. I apply a pulse on carbon, right? This is my pulse on carbon. And now I'm decoupling on the proton, which means that I'm keeping 2 frequencies on at this, well, not at the same time, but at a different time, and I'm detecting here. This, there is no problem. I can listen to 106.4, but I can casting at 97.2. So that there is no problem because they are at 2 different frequencies. And if so, this is 400. Let's imagine if this is 100, this is 400. So this is at 400 megahertz and this is at 100 megahertz, so this is no problem. There won't be any interference. And look at what happens. All your signals have gone up. So all C13 spectra are gathered this way. And this is something that is. So I said, so now we have chemical shift, we have J coupling, and we know how to remove J coupling so that you can tell which 2 things are close together in space, close together or bonded to each other. And now there is another experiment which is a beauty. And this is strychnine, by the way, which can tell you. So not only when a molecule folds on itself, for example, right? So here is the strychnine. Now this is a proton 20 here. Now this could in principle come close to proton 15 here, but they are not attached. So there is no J coupling. But you can have 2 protons which are come to get close together in space because of the way the molecule is built of its 3-dimensional structure. As structural chemists, we are interested in knowing this. So now, but there is no J coupling. So I can't use J coupling. But there is a way of communicating between this. And this is related to what I said. When I have 2 dipoles at 2 different locations in space, they affect it in a second order fashion in liquid state. So now when I do this experiment, which is done by this way, so now this is all proton, mind you. Before I come with that 90-degree pulse, I apply a radio frequency. So I do a radio frequency irradiation here, right? And then I record the spectrum. I then move this irradiation there. That is, it doesn't matter. You can remove this. At least theoretically, you can remove this. But experimentally, it's better to remove it, move it from here to some other point. And if you look at the difference, look at the difference. When I keep this irradiated, what it's telling you is that this proton, and this proton, and this proton are close to this proton in space. So this tells you what is the geometric location. But they are not coupled, necessarily coupled. They could be J-coupled, but this is not necessarily coupled. So this tells you, gives you immense structural information. This is telling you, look, which 2 protons are close together in space. And this is an experiment called NOE difference, nuclear Overhauser effect. This is something that you might encounter, but is routinely used by organic chemists. And I think I'll just be able to talk about 2 different things. That is, one is called polarization transfer, and with that I will close. See, I've been repeatedly saying the carbon 13 has a frequency which is 1/4 of that of the proton. And we say a carbon 13 also has a natural abundance of 1%. So if you looked at this, this is the equilibrium distance of a carbon 13 attached to a proton, let's imagine. And what we are saying is that the signal, so this difference here is the proton's difference. And the thing that is different is whether the carbon-13 is alpha or beta state. And you can see that this difference is 8 delta. Both protons have 8 delta, but the carbon has only 2 delta, which means if it is 100% abundant, population difference in C13 is 1/4 that of the proton. But imagine what happens if I invert these two. That means that these are 5 black dots. These are 3 3 open dots. If I switch the two, the 5 black dots go here and the 3 open dots come here. Now, if you looked at the carbon, this has -6 delta, which means that the ground state has lower energy, lower population than the upper state. And in this one, this is 10 delta. Earlier, it was 2 delta. Look at this. This is 2 delta. Now, this has become 10 delta, which means that the carbon-13 intensity has grown relative to the proton. Proton is, think of it, is a big reservoir. And now, when I did this experiment, carbon-13 intensity has gone up. And this is fantastic. I can use this to increase the signal of carbon. And this is what is done typically. So no carbon-13 spectra is typically recorded in the way that I earlier talked about. And here's the experiment to do this. And I'm illustrating this specifically for two things. One, you look at, and this is answering Shivangini's question. Look, I can manipulate the signal by manipulating these things. And by doing this, I'm able to get polarization transfer from proton to C13. And look at this experiment here done with sucrose. This is 13C spectrum with no decoupling. And this is 13-3 spectrum done with this sequence. And look at the signal. This signal, for example, is at least 4 times or maybe 2 or 3 times bigger than this. So you get enormous. So all C13 spectra nowadays are recorded in this fashion. So you can essentially manipulate what we want. And with this last thing that we can do for small molecules is that you can use this polarization transfer to detect what kind of carbons that you have. Look at this. If I did this experiment, which is achieved by this pulse sequence, again, look at, don't worry about the details of the sequence. That's for people like us who will worry about this. And you can see that I can identify, you have different kinds of carbons, right? I have quaternary carbon, I have a CH, a CH2 methyl, methylene, and methine. And you can see that I can differentiate. So look at this. If I did depth 135, the methylene comes negative, whereas the methine and methyl come positive. So I can use this to differentiate between whether I have methine, methylene, or methyl group with this sequence. So this is about the kinds of things that people will typically do. And I think at that stage I will stop. I could have discussed a little bit of two-dimensional NMR, but maybe I'll leave it to the experts like Vinesh and Ragottama and Suryaprakash to talk about it, because I've already reached the end of my time. So I think I'll stop here at this moment. If you have any questions, I'll be happy to answer.
Wonderful, Dr. Narayan. Thank you very much for the excellent talk. And the session is now fully open for discussion. Have some queries. We would be very glad to receive your queries and address them.
Yeah, I noticed that Bharadwaj is here. Bharadwaj, his name I
Please, sir,
missed his
please proceed, sir.
Yeah,
Please
no,
proceed.
these people, Bharadwaj and Vinesh and Ragottama and Suryaprakash are probably going to talk about this more. They talk of very heavy duty samples. As far as I'm concerned, anything greater than proton or hydrogen atom is too difficult to understand. So yeah, so they'll talk of interesting examples. Okay, let me look at the chat box. I would like to know the topics. Okay. Okay, yeah, I'll just show you that in a moment. Once, I'm sorry about that. Yeah, I had something listed. A lot of the things. Maybe one of the others will talk about it. And here are some of the works that might be of interest. There's also another book from which this is derived. I think you can take a look at that, from this one here. Both of these are quite practical. I think this is a little bit more theoretical, but otherwise I think all of these are good examples. Okay, so I think anyway, if required, I can always send this presentation.
That's
Okay.
perfect. We shall share.
Okay, Sachin Balara. Again, the concept related to Faraday's law. Okay, this is Anvita has asked me privately, but I think I'll answer the question. I'll answer the question in public. Okay, I will do it just waving my hands. I hope that's okay, Anvita. So let's imagine that I have my magnetization here. I have a magnetic field here. My coil is somewhere. That's a solenoid. Now, when I remove the RF pulse, the magnetization is in this direction. This thing will go around like this because this magnetic field exerts a torque on this, right? So this will go around like this. And this will do it in natural, right? Because there's no perturbation. The perturbation has been removed. So this thing will have to process at its own frequency. And when it does that, I have a coil, let's imagine, a coil which is around it. That will cut the lines of force, right? So this cuts the lines of force. And we know from Faraday's law, when I have a magnetization which cuts the lines of force, it generates a voltage. And so that's what it is. Is that okay? I hope I answered the question. Are the electrons using any orbitals for their motion? Well, it doesn't matter which orbitals they are. Orbitals anyway is a concept that we have in our head. It is not something the electron doesn't know which orbital it is. The electrons are there. They are just electrons. So, but yes, and they are, as quantum mechanics would say, it's just anywhere between 0 and infinity. So yeah, it undergoes motion, and if it undergoes motion, it generates electrons. Well, they interact with the nucleus. They interact with the nucleus, and that's something that if in our case, okay, there's a difference. Okay, Ayan is asking. There is if you have a paramagnetic molecule, then in our case, the electron spins, we are looking at diamagnetic systems. So there is no unpaired electron. So there is no per se interaction between the electron and the nucleus. But the electron does play a part in an interaction. And that's what I talked about. This interaction between two nuclei, which are dipoles, is through the intervening electron. So in that sense, there is an interaction. But other than that, if you had a paramagnetic system, yes, there is a hyperfine interaction between the electron spin and the nuclear spin, which is called the I dot S interaction. But we are talking of diamagnetic systems where where this does not exist. It doesn't. Yeah, the electron doesn't have. That's not. Yeah, what you say is true, that the electrons, although it has a low probability of being at the nucleus, but we also know that so yeah. So that's a good question. This chemical shift, or yeah, that happens is you can differentiate two types. There's one where it is called the Fermi contact interaction, where because if the electron was in an s orbital, that has non-zero electron density at the nucleus, so there is an interaction of that. But there is also an interaction involving the higher excited states. So that is that if there is any orbital motion, orbital angular momentum, that will take care of it. Yeah, but these are very small. You realize this. I mean, it's not as if this is a huge interaction. You have to get this right. We are talking of NMR frequency of the hundreds of megahertz, let's say 100 megahertz, 400 megahertz, something like that. And the J coupling is of the order of tens of hertz. So that's at least 8 orders of magnitude smaller. So it's a small interaction, a very, very small interaction. And that's another one of the beauties of NMR, is that you can measure such small interactions. So that's something. Okay, what is the guess factor? Guess factor. I think this Prashant Chaturvedi's question. Guess factor, it's, I guess, from all frequencies from minus infinity to infinity, one at a time. That's what I'm doing in my head. But on the computer, it doesn't, you don't do it like that. I'm saying that I guess a frequency, right? Yeah, I'll start at negative infinity. I'll do it systematically and go all the way to positive. And one of them will match. So that's what is the guess factor. But I don't do it like that on a computer. On a computer, it's done very, very quickly. Like that, you can do it. Okay, and on the historical development of NMR, my God, I'm not the right person. I'm not a very, well, I know a little bit of the history of NMR. Well, if you want to know of NMR history, the first person to measure this was Isidore Isaac Rabi, but he measured it in the gas phase by an experiment which is called a Stern-Gerlach experiment. So Rabi measured this long time ago in the 1930s. But in the condensed phase, the first people to measure it was Felix Bloch at Stanford University in Western United States, and Ed Purcell, who was at Harvard University. That was in 1946. It's back-to-back papers in the Physical Review in 1946. And then 1966, well, there are some very seminal developments due to Erwin Hahn in between, somewhere around 1950s. He measured the J coupling, he measured what are called spin echoes. He did some fantastic experiments. In 1966 is when Fourier transform NMR came. Two-dimensional NMR came in 1976. And after that, it's been an explosion. So that's, in 2 minutes, the history of NMR. Okay. Why we need to use different nuclei? Well, there are various reasons to use different nuclei. One is that proton has a very small dispersion. So if you looked at a complicated molecule, even sucrose, there are so many proton signals, it's very difficult for you to differentiate one proton from another. That's one reason to differentiate. And we also need to know, and I didn't talk about it, I mean, one of the things you can do with two-dimensional NMR is you can find out which proton is attached to which carbon. So that's something that we can find out. So there are lots of reasons for that, as to why one uses other nuclei. And I think if you listen to Vinesh or Bharadwaj or Surya Prakash or Raghotama, they'll talk of nuclei. There'll be enough nuclei to make you sort of hallucinate. They'll do proton, carbon, ethers, proton, carbon, nitrogen, phosphorus, everything under the sun. I've only talked of proton and C13. But yes, finally you need dispersion, right? You can't, if everything, I mean, the example that I said, if all the students were sitting on the back row, the teacher cannot differentiate whether it's roll number 1 or roll number 10. That's one reason. Okay. Let me see again.
One more question is how electrons interact with, I did not know whether I missed, but how electrons interact with the nucleus, as it has very low probability to be where the nucleus is.
Yeah, I did sort of try to answer it. There is no direct, first of all, I repeat, we are looking typically at diamagnetic molecules, although these days paramagnetic molecules are becoming very, very important. But we are looking at, I was paying all attention only to diamagnetic molecules. So we don't have unpaired electrons, but electrons also have a spin, right? And they also behave like dipoles, and they are undergoing motion. So the interaction is not to zeroth order. There is no interaction between the electron and nuclei, but because they are charged objects and etc., there is an interaction, and it's small. And that's what I said. It's 8 order of magnitude smaller than the big interaction. So it's a small interaction, but it's there. How it interacts is through a magnetic interaction. It's not a not an electrostatic interaction. So it's not very big. It's magnetic. All magnetic interactions are typically scaled by a factor of Q over C relative to an electric interaction. So these are very, very small interactions. One of the other attractions of NMR is because of these small magnetic interactions, they're not affected as much. Yeah, so it's small there, it's there, but it's small, very small.
More queries, please. Please, more queries. So in between, I have one or two queries related to our current research programs. Because this is related to the query by one of the examiners, one of the reviewers of one of the recent articles. So, how do you correlate this NMR investigation with the kinetics of reactions?
Oh, well. There are NMR techniques for that. So, yeah, you look at what is called chemical exchange. It's again, I didn't talk about those things here, but it's a very quite routine. We can do experiments. You do it as a function of temperature. Often you can tell how the spectrum varies. From that, you can get some idea of the kinetics. Yeah, that's possible. It's possible. I think your question,
like
what I would suggest is
high pressure NMR or like.
Yeah, high pressure NMR is also possible, but you and I cannot do it. Maybe, I don't know if IASC has. You have to have special apparatus for doing that. I won't be able to do it.
Okay.
Maybe IASC does it. I don't know. We have to find out. They used to probably do it in some labs, but I don't. But I think what I would suggest is, since that's, you could just write me a mail and then we can think about it.
Great, sir. Wonderful.
Yeah. We don't want to bother other people with this. Yeah, so
yeah.
I'll be happy to answer that.
Thank you. Please, more questions, please. More questions.
No, I don't want to force questions. If there aren't any, we'll close. I think I've already.
This platform, since it is being attended by more than 180 people.
Yeah, I noticed very good attendance. I don't know. Well, these things we never know what.
And that is why we rate it as very good, because it is useful to many students, college teachers, and students are now listening to you.
Well, I hope I haven't disappointed.
Sir, if you give me a freedom, I shall ask one more question regarding, you said it, but primarily, basically our group works on macromolecular structure. So
you know what? Then I think the best is to talk to Bharadwaj or Vinesh. These people are experts. I can't differentiate a protein from a nucleic acid from a hole in the ground. I don't know what they are. So I think I might be the wrong person. You can talk to Bharadwaj. I mean, they're experts. They're leading figures in the field. Right. Okay.
So I request all the participants to have more questions. If there are no more questions, we'll try to wind up with the permission of Dr. Narayan. And shall we move? No, okay. So, Dr. Narayan, we are extremely thankful to you for the wonderful lecture you start. The building up of the concept was extremely beautiful, so that those who attended, I'm sure it will be highly useful, particularly to those teachers who teach MSc students the fundamentals of NMR. So we are, sir, deeply thankful to you, and we would wish to invite you to the NIT Calicut campus offline when we get time. So, sir, with your permission, I will invite the control room people to have the further steps. Thank you, sir, very much. Over to the control room, please.
Thank you so much, sir, for such an informative lecture on understanding NMR methods for structure elucidation. Now it's time for lunch break. I request all participants to resume here at 1:45 p.m. sharp for the second session by Professor Abani K. Buyan from University of Hyderabad. Thank you.
So may I leave now? May I leave?
Sir, once again, Prasad, on behalf of NIT Calicut, a big thanks to you, sir.
Thank you. Thank you.
Thank you, sir. Thank you very much.
Thank you all delegates. Join us by 1:30. 1:40. 1:40.
right? Share. And then start this. Oh, okay. So I am there. Yeah. So let it be like this only. Henceforth, I will just project the full screen maybe. 1 minute. Project the full screen and then I go, right? Yeah. All right. Yeah. So shall I stop right here and then I'm here only. So right now it is what time? Okay, yeah. All right. So anything, you just give me a phone call. Okay. All right. Okay.
Sir, can you hear me?
Yeah, I can hear you.
Yeah, you are also audible. No problem, sir. That's fine,
Okay.
sir.
Is that sound good enough or I'll lower
Yeah,
down the volume?
it's fine, sir. It
That's
looks good.
fine. Yeah, I'll just tidy up a little bit. There's another too many computers here, so
Okay, sir.
I'll remove some computer from here. Yeah, I will go to the screen first. Okay.
It's already there. You just need to make it full screen. That's all. Yeah, yes, sir.
Welcome back to the second session of now. We can move on to the next session by Professor Abani K. Boyan from University of Hyderabad on topic calculation of NMR structure using NMR spectroscopy. It's my pleasure to welcome Dr. Anuj Evagis, Assistant Professor, Department of Chemistry, NIT Calicut, to chair the session. Over to you, sir.
Yeah, thank you, Sarah. So, Srilaya. So, it is my great pleasure to introduce Professor Abani K. Buyan, or we fondly call AKB. Okay, so Professor Abani obtained his PhD from University of Pennsylvania in 1995 And after that, Professor Abani worked as a visiting fellow at Tata Fundamental Research, Institute of Fundamental Research, that is TAFR, as a scientist, and at Institute of Genomics and Integrative Biology also. Currently, Professor Abani is Dr. Abani is working as a full-time full professor at University of Hyderabad, and his research interest includes understanding protein folding and relaxation dynamics, and application of soft matter principles to protein phenomena, and the structure and function of eukaryotic ribosomal proteins. Okay, so. Yes, sir. So I request Professor Abani to take over the session. Welcome, sir.
Yeah. Hi, everyone there, Anuj and everybody else. Thank you for inviting me to speak in this workshop. It's really, and I know NIT Calicut is also one of the renowned institutions. So it's a privilege to be talking to you, speaking with you about protein structure calculation using NMR. But a few of these things we do ourselves in our lab. So we will go over what it all means. I will not remove my mask because this place is still not very safe. So I'll be masked all the time. I hope that's okay. You can stop me anytime you want to, and I would be happy to answer all the questions and queries. I will try to go a bit slow, and hopefully in about an hour's time, we will try to finish it off. Okay, this is actually, there are many other material. Let me get some from here as well. Okay, so I also presume that the audience has some basic knowledge of NMR experiments. That will be helpful. And I will try to point out class of experiments that we need in order to calculate protein structure. All right, the very first thing we do when we have a protein, we run a COSY experiment. A COSY is a it can be heteronuclear as well. It's called correlation spectroscopy. Here, the first 90-degree pulse takes us to what we call evolution period, where the magnetization in the transverse plane are labeled, and then they are mixed by the second 90-degree pulse, and then we detect the signal. Fourier transform the signal, and then we get this the spectrum. The most important part of a COSY spectrum. Okay, what I'm trying to talk right now is the very basic level of the fundamental aspects of doing protein structure. So the region of interest here is what we call a fingerprint. This is a Fourier transformed COSY spectrum. The region that is of fundamental interest, that is this fingerprint region. A fingerprint region means the amide hydrogens, or the amide region, is correlated with the aliphatic region. Aliphatic region means where the alpha and beta proton, there isn't it. Okay, for example, now one thing is there, we call it a fingerprint region because virtually each amino, suppose we have 100 amino acids, virtually all of them often glycine shows 2 peaks. But let's say, again, let's say glycine, we just take for the time being just 1 peak. So we'll have 100, in principle, 100 peaks in the fingerprint region. That is what we call a fingerprint region. That is the NH region. And let's say that the protein is dissolved in water, where a little bit of deuterium oxide D2O just to lock the signal. So these amide hydrogens will not exchange out with the solvent. Each of those amides, that means from each amino acid, one amide, they will resonate in the fingerprint region. And then from the fingerprint, it just so happens, this is an exercise that we have been doing it ever since I was a graduate student. For example, each of these amide resonance from here, they can be connected to the respective, that means of the same amino acids, beta proton and the alpha proton. So suppose here this is the NH cross peak, correlation peak of one amino acid. From there, we can trace out. Sorry, there's a little problem here. Okay. Sorry about that. All right. So from there, we can trace out, from here, we can trace out the beta and the alpha and the beta region like that, even to gamma as well. So this tracing of this correlation that is, it should have had a laser pointer, but that's fine. So we go from here and then trace out the amino acid all the way to beta, and then to beta, and then to alpha, and then to alpha to beta, and then gamma region. This is an exercise actually as a graduate student we were supposed to do. And going back to some like 30 years ago, these are the exercise. You can see from here some of the things that we trace out this pattern of connectivity of the amino acids. So, okay, fine. We got one amino acid here that we connected from the NH to the alpha to the beta to the gamma. So this pattern is unique for an amino acid. So in this case, by tracing this pattern, we figure that this is a valine residue. Similarly, we can trace out from each of these okay, from each of these. Okay, I will ask someone to get me a laser pointer, but I hope how to do this.
Sir, actually, you can just right click on the screen.
Right click on the screen here.
Yeah,
here.
and it will show the laser pointer, sir. You can see it there.
Which one?
There itself, laser pointer will come. 1 second, sir. I'll just exactly tell you.
Okay.
Sir, if you come down, there is pointer options. Next is there, then see all slides, zoom in, screen, and then there is a pointer. Pointer options.
Okay, well, restore window. Shall I? Okay, 1 minute.
So you can just right click with the mouse. Nothing else, just right click.
Okay, well.
No. So you're moving ahead.
Right click where? In the screen?
Yeah, in the screen.
Okay. No. All right, don't worry about that. I'll manage somehow.
Sir, it's very easy because you're clicking on the left button. You need to click the right button actually.
No, I can't get it. Okay, let's see. Don't worry, it's fine. I'll just try to manage. Unless somebody comes, then I will try to get it done that way. That's fine. So, or if you allow me just 5 minutes, I'll go and get a laser pointer.
Sir, actually, one more second. Sir, if you look at, you bring your mouse to the bottom of the screen.
Right.
There you can see some icons at the bottom. There are left. No, you just need to move the mouse only. Don't click on anything. Bring the mouse to the bottom of the screen. So you see that. Yeah, left side, extreme left side, where the mouse pointer is there, the other end. You can see some of the icons actually. I can see it, sir. So only the mouse, don't click on that one. You can just bring the mouse. Yeah, you can see it on the other end of the mouse, bottom. Yeah. Now we can.
These are the icons, video options.
Yeah, no, sir. Actually, below that University of Hyderabad logo, you bring your mouse, sir.
Okay.
Yeah, slightly lower.
Slightly lower.
Still a little bit lower.
Lower. Oh, okay. Now I see.
That's the third button. Third button. Yeah.
Third one.
Yeah, you can take the laser pointer, sir.
Laser pointer.
Yes, sir.
Oh, here you go. Hey, thanks, Anush. Thanks a lot. Because I do in a different, I use a physical laser pointer. Anyway. All right, thanks for that. This will be much better now. So here we have a valine residue starting from the NH resonance. We are going to alpha, then beta, then gamma. Similarly, we'll go to another from the fingerprint region. We'll trace out the connectivity for another residue and say that that is tyrosine. Go to third one, tryptophan. Like that, say for this 100 amino acids, we'll have the connectivity of all those 100 amino acids. So we know that these are the residues, and then we have the assignment for these residues. For example, valines, C alpha will resonate in this at say 4.22, C beta at 1.55 or 2.55. That way, we just catalog all these chemical shifts. So we have virtually assigned all these amino acids in our protein. But so far, we have not been able to get the connectivity of these residues, like which residue is in sequence, no? Which residue follows each one. Well, if we are smart a little bit enough, we can actually go back to the amino acid sequence, and often, just by doing certain kind of hit and miss procedures, we can often determine the sequence in which these amino acids are there in the protein. All right. Now, the cozy fingerprint region that I was talking about within this circle, within this box in here, or same thing, in a two-dimensional spectrum, this is like the other side, the symmetric, the symmetry of this fingerprint region is in here as well. So, yeah, then this is the fingerprint region that I'm showing here. All these residues have been assigned one by one. This is just a hypothetical case. One thing is there, which we will come to use often, is that a cozy spectrum, the cross peaks, they appear like the positive cross peaks and the negative cross peaks. So these are the positive ones, and these are the negative ones. These are the diagonal peaks, and I have simulated these cross peaks and diagonals. They look like this is the cross peak. As you see here, negative, negative, positive, positive. This is a cozy multiplet. That's what we say. The negative, negative, positive, positive. So each cross peak in a cozy spectrum is actually a multiplet, quartet kind of multiplet. And the diagonals are these ones. These are the dispersive signals. They are the diagonals. as we show here in the diagonal of the COSY. And then because it is a multiplet, there are 4 positive, positive, negative, negative. When we plot the spectrum, we see that these ones, like these ones, these two, they're positive or negative, and this is the positive, positive, negative. So a COSY spectrum, the cross peak is a multiplet cross peak. Now, the utility, I mean, at this point, I should also say that the between the center of this peak and the center of this peak, in principle, that is the J value. That means the spin, the coupling constant. Okay. All right. So once we have this fingerprint region here, and then we have assigned these residues, which is what this is H15, histidine 15, C115, different 62, and all that. The fingerprint region we know. Now, sometimes it may so happen that 2 residues, their resonances may overlap. If that overlaps, then there is an ambiguity. In other words, we cannot trace out the side chains of that amino acid because they're overlapping. If that is the case, then we do a second set of experiment. That's what we call total correlation spectroscopy toxic, or DQF. That means the multiple quantum filtered experiment we do in order to remove those ambiguities. It's just because the side chain of valine is different from the side chain of some, say, aspartic acid, and a toxic experiment can in principle differentiate whether the protein is whether the protein is whether the amino acid is valine or aspartic acid. Okay, so all right, so this is the toxic experiment. So what we have learned so far is that by using COSY, DQF means double quantum filtered COSY, and TOXY, we can remove ambiguities. But COSY is the basic experiment. That's what we do in order to assign these residues. So at this stage, we have the J-coupled NH, C-alpha H, and C-beta H resonances for each amino acid in the protein. Once this assignment has been done for all the amino acids in the protein, in the next step, we go to the through space correlation. Now stitching these amino acids, like which amino acid follows which one, or which one precedes which one. So this concatenating the amino acids, stitching them up is what we do. And then okay, the way it is done is the following. All right, this is the NOSI pulse sequence, and this is a typical NOSI experiment. We'll come back to again NOSI. Here is the evolution time, the mixing time. We collect a NOSI spectrum, and each cross peak in principle in the NOSI spectrum is a nuclear Oberhauser buildup of the 2 residues that couples to produce the nuclear Oberhauser effect. Now, say here is one amino acid residue. This is the C-alpha. This is the side chain. This is the C-alpha proton. This is the NH of that, and this is the CO of that amino acid. Now notice here that this amino acid is the IF amino acid, and this is the I plus first, IF plus first amino acid, and the NH of the I plus 1F residue, that will show an NOE connectivity with the C-alpha proton of the preceding residue. Same thing will happen, say, for the CH alpha residue will will produce connectivity, NOE connectivity with the I plus second residue, NH of the I plus second residue. So CH, NH, CH, NH, CH, NH. So like that, IS, I plus 1, I plus 2, I plus 3, I plus 4, the residues can be concatenated. Why? How can we do so? We have done, because we have the assignment that this is, for example, say some residue, aspartic acid, for example, and this is connecting to the I plus first, that is saying whatever it is, the glutamic acid. So the D alpha N, we call it a D alpha N. It's the about 2 angstrom apart, 2 protons here. Similarly, there can be NOE connectivities from the beta proton to the NH proton. So these are all the connectivities. Some of them are what we call kind of long range. That means IS to I plus third residue here. This connectivity also we can have. Now, because we know the C alpha protons resonance, and we also know the NH resonance from the fingerprint region. So if these two these two peaks produce an NOE cross peak, then we know that that NOE cross peak is due to this residue and I plus first residue. Or it could be, say, if we know this one, then the connectivity, D alpha and connectivity is between I plus 2 and I plus third residue, right? So because we already have the assignments available, and now in a NOESY experiment spectrum, we see the cross peaks building up, so we can stitch at least pairwise connectivity of these amino acids. So here it's written here, connectivities grow progressively, the proximity of residues increases, and these are there are certain signatures also we can use often, that the D alpha N cross peak is most intense in anti-parallel beta shape, but there these patterns are often observable. All right, so these are the sequential D alpha and connectivity. Notice now here, this is a small region. This part is expanded in this panel here. We notice that 128, 129, when in sequence wise, 128th and 129th residue, they together. This is a NOESY connectivity from these two residues. This is the NOESY connectivity, D alpha N connectivity between 42nd and 43rd residue, between 18th and 19th, 85th and 86th, 71st and 70th and 71st, and so on and so forth. So we have this D alpha N connectivity in a pairwise manner, each presiding residue to its following residue. That is what we pick up from the NOESY spectrum. All right. Now, there is something very interesting that we have to do. Often it is possible to connect this pairwise NOE connectivities in a way so that all the residues in a stretch, in a sequence of a sequence of residues, they can be stitched up or concatenated. Here is an example. Again, I'm enlarging this part of the spectrum here. Notice here, it's very interesting. Just notice here, from to 90th, this is the D alpha N connectivity. From here, we just go horizontally to 90th plus 91st, then 91st to 92nd. Then from here we go and then come back to 92nd and 93rd. I don't know whether you can see this on the screen there. But then again, from 92nd to 93rd, we go to 93rd, 94th, 94th to 95th, 95th, 96th, 97th, 96th, 97th, 98th, 99th, like that, all the way to, yeah, 98th, 99th to 99th to 100th amino acid. So what have we done is that we have connected residues 89 all the way to residue 100. When this happens, this must mean that this is the stretch of a secondary structure in the tree. Similarly, one can pick up from somewhere and try to find out this connectivity. Here, all horizontal and vertical movement of these residues. From vertically we move, then horizontally we move. Vertically we move, horizontally, vertically, horizontally, in an effort to concatenate, stitch up these residues. Once we are able to do so, that means we have gotten a secondary structure stretch. Similarly, there could be other regions. If we work a little harder, we'll find out another stretch, third stretch, fourth stretch, and these are all secondary structures of different kinds that we have been able to find out. Okay, so then as we said before, that measurement of J values means you have heard of Karplas equation. They're A, B, C. These are the constants empirically determined, and theta is the torsion angle, the backbone torsion angle. So if we can calculate the J values from here, from the cozy spectrum, because it's a multiplet structure. So from here to here, this is the J value, this is the J value, this is the J value. So if we have those J values, then we calculate the torsion angle, backbone torsion angle. So this is one exercise we do. All right, now let's recapitulate that we have been able to establish the secondary structure patterns by horizontal and vertical movement. And then we have the J coupling, that means the backbone torsion angle. Then the distance between two nuclei, two protons, for example. This is again done with the nuclear Overhauser experiment. Now in NOE, two coupled spins, the transfer efficiency or efficacy is directly proportional, inversely proportional to the distance between those two spins. And there is a tau c. Tau c means a correlation time, that's a tumbling time of the protein. But tau c is not a very easily understandable parameter quantity, because the side chains have different tau c. The whole protein globally has a different tau c. The flexible regions, which tumble faster, right? So and the stiff regions, they tumble slow. So tau c determines on those, depends on those tumbling times. Then now there's something called NOE buildup. I will have to spend a little time, but I don't know whether I'll be able to do so. But at this point, so a minute. Okay. Yeah. All right. That doesn't matter. Okay. Anuj, you can hear me now?
Yes, sir. You're audible.
Okay. No problem. Is
So if
this
you can
equation
sit
fully
close to the
shown on
mic,
the
then
screen?
it would be more audible, sir.
I'm sorry.
If you can sit close to the microphone.
Okay. All right. Is that
Yes.
better?
Yeah. Yes. Better, sir.
Okay. So the distance is measured by doing a series of NOE experiments. I'll try to explain to you a little bit better way. Okay. You know what? The NOE experiment. Notice here that this is T1, the evolution time. This is tau m we call mixing time. What can be done is that this mixing time can be varied, say from 20 milliseconds, 30, 40, 50, up to about say 150 or 300 milliseconds of mixing time. And each time we change, I mean, that means we have, say, by varying the mixing time, we have collected, let's say, 7, 8 noisy spectra. From those noisy spectra, the cross peaks we quantify, and those quantified cross peaks, when they're plotted with the mixing time, you see here we have done an experiment with here 9 mixing times and the cross peak. This is a cross peak from two particular spins. This is from another 2 spins, from another 2 spins. Notice here, this initially, this actually comes from the Solomon's equations, but I will not go into those. The build-up means how the NOE intensity, cross-peak intensity builds up, and then it decays. When it decays, the relaxation effects set in. This experiment, one of my PhD students did recently, for example. Notice here that NOE is building up with the mixing time. So if we have the slope or the initial buildup rate, we call it a buildup rate sigma. That buildup rate, if we know the tau c value, then we can calculate the value of R between those 2 spins, which produced this NOE cross peak. So in this case, the slope here, that is the NOE buildup between 2 protons, right? And then by knowing that slope and tau c, we can always estimate. Tau c is coming about, 10 raised to the power minus 7, minus 8 seconds, that kind of tau c. Then we calculate the R, the distance between. One trick is that it is always good to have as many distance constraints measured by this method as possible. The more number of distance constraints, the value of R between NOE coupled spins we have, better will be the structure calculation. So that is how we do NOE buildup and correlation time. And as I said, the tau c is a spoiled play, because if tau c is short, a tau c can be short when some part of structural part of the protein somewhere is very, very flexible. If dynamically really flexible region, then the tau c will be shorter and NOE buildup rate will be small. Often at times one may not even see much of NOE buildup if the region is very, very flexible. But for stiff regions, it's pretty good actually. We can calculate NOE distance to within 1.5 to 2%, that much of accuracy we obtain. All right, what have we done? Let us recap. We have found out the stretches of amino acids which form a secondary structure element. Now, then we also collected some of the NOE distances between these pins. Then it's very easy. At this stage, a coarse and qualitative model of the protein can be built even without using a computer. You can do it manually. How to do it? As I said, that we have these stretches of amino acids forming a secondary structure element. This one, let us say that there was another stretch which is which is because
Hello, sir. Sir.
Anuj, it looks like he lost the connection.
Yes, ma'am. I'm calling you.
audio is not coming. Right? Now it is coming. Am I okay? All right. You can hear me now?
Yes, sir. Yes, sir. You're audible. I'm cutting this call, sir.
That's right. Yeah. Okay. Sure. Yeah. Okay. I'm sorry. There's some little technical problem here, but I can go over again. See, what we have done is that we did this NOE experiment, and then from those NOE build up curves, we found out the slopes. I mean, and from the slopes, we calculated the distance between two spins. All right, and by knowing this, the secondary structural elements. Now I have to find my 1 minute. I'll find my laser pointer. Here you go. And then we have these secondary structural elements. Then yeah, we just quickly calculate, find out the NOE distance between two spins from one each from the secondary structure element, and we can then put them, orient them in space. And this is what we call a manually built, coarse and crude qualitative model, but this model is good enough as a foundation. At least we know that these secondary structure elements, they are oriented in this particular manner. All right. Now that is what we did. We have the secondary structure elements oriented. Now the tertiary structure. For that, what we call a distance geometry calculation. And then in the distance geometry, it's, you know what, distance geometry is just a mathematical tool and nothing more than that, which just gives us a structure consistent with all the NMR data that we have, NMR distance constraints we have. The distance geometry is something that to calculate, it's an algorithm, or it's a procedure, it's a tool, a mathematical tool, matrix we use most of the time to calculate the structure which will satisfy all the distances that we determine. Totally automated now. There have been, like, plenty of softwares have been written already, and there is hardly any problem. Only the input files, I mean, from our NMR data, there is a format. In that format, we just feed in our data, and the program, the software calculates everything. Nevertheless, I'll just go over in quick 2-3 steps the meaning of this distance geometry. In step 1, suppose the protein is a protein, there are 100 amino acids. So we have a collection of endpoints. What could be those endpoints? Each amino acid, suppose 1 point, right? So there are 100. And out of one amino acid, we can choose that we will have the C alpha carbon as the point. So for 100 C alpha carbons in the protein, we have 100 points. That means N is equal to 100. So it's pretty clear the molecule is represented by a collection of N points, all right? Say 1 point per residue. This should read step 2. It is written 1 because I copied. So step 2 is that the geometric, that means that, oh, step 2 is here. That is a little, you ignore this. So step 2 is here. Now we have to have these geometric constraints. What does it mean? You know what? The geometric constraint means we have two matrices, say one lower bound and one upper bound. Okay, fine. We calculate a set of 3D Cartesian coordinates. So we have N points, right? We have 100 points. So I means 1, 2, 3, 4 up to N. So for 1 point, that means 1 alpha carbon, or for 1 amino acid, let's say we have, or 1 spin, we have the Cartesian coordinates x1, y1, z1, x2, y2, z2, x3, y3, z3, and xn, yn, zn. So this is the what we call a Euclidean distance between 2 points. That means, say, point ith point and jth point, or amino acid 1, amino acid 2, or point alpha carbon 2, alpha carbon 3, like that. So that is the Euclidean distance, and that has to fall between these constraints: lower bound matrix, upper bound matrix. D is what? D is the element of the matrix. So because we have N points in our exercise, we'll have an N by N distance matrix. So where upper bound means the upper bound matrix U will have elements Uij, ith, and jth. Similarly, I plus first, j plus something like that. So each successive points in the protein or in the space, they will have their matrix elements. And then similarly, the lower bound matrix will have elements Lij. So this is what we call the calculation of these Cartesian coordinates. In step number 3, we complete the U matrix by, initially we often assign a large value, all these the elements in the matrix that we don't know. Yeah, we assign them some large value and then apply this triangular inequality. That means for 3 residues I, J, K, the Uij element in the U matrix is less than equal to the Ik element of the U matrix and the Kj element of the U matrix. We do this is for the upper bound. We do the same thing for the lower bound matrix. So these are the elements, and this is for 3 points that we took. So this is how we calculate the UNL matrices. Again, notice that each of these UNL matrices, they're N by N matrices. Okay, now we randomly choose the the matrix that we calculated, that we choose them one by one. You can suppose we calculated 100 or 200 N by N matrices by varying the elements initially that we don't know. So then we choose, say we have 200 matrices or 200 of these conformers. Each matrix corresponds to what we call a conformer. So suppose you have 200 conformers, 200 matrices, then for all Ij, if Lij is less than equal to Dij is less than equal to Uij. What is Dij? This is the distance between 2 points, the ith and jth point, or ith spin and jth spin. And this is the lower bound matrix corresponding element in the lower bound matrix corresponding element in the upper bound matrix. So for all I and j, we randomly choose this distance matrices, distance, and then this is the stage that produces a variety of conformers, one for each d. So the matrices which did not violate our initial conditions, and then we randomly choose them, say out of those, the 200 conformers, we have 200 conformers, so 200 kind of flexible or sort of sausage structure. Now, each of these structure conformers, they're they're judged or they're weighted statistically. Which of these have better statistical figure, better statistical credibility? So from those 200 conformers that we generated by randomly choosing different matrices, out of those 200, say we took 10 or 20 or 30 best conformer. So this is what is shown here. The best 20 structures out of those 200 conformers that we generated by randomly choosing the n by n distance matrices. Again, I repeat this. It is good to know the distance geometry calculation, although these have been known for many, many years, even before NMR came into picture. Distance geometry is just a general mathematical tool that can be applied for many different applications. And these are all, like, as I said, these are all automated. One doesn't really have to do much, only input the figures, and then one has the conformers generated, all right? So yeah, okay, so here we are. We have like 20 conformers, statistically best ones, best out of those 200 initial conformers we generated by randomly choosing these matrices. Out of those 200, again, we do, okay, there is something what we call, this is okay, good enough up to this point. Sometimes in order to have even better agreement, we choose out of these 20 the best structure statistically. Statistically means root mean square deviation. Oh, I have written here. Let's look at the statistics and choose the one with best RMS, the root mean square deviation, the lowest one, and which doesn't violate. We also go back and forth between the phi-psi map, the values, whether those values are in the allowed region or not. That also we calculate, okay? And if they're allowed, then only we validate the structure. If they're not allowed in the phi-psi map region, then we discard that. Another way of, I mean, this kind of refinement can also be done by what we call restrained molecular dynamics simulation. You know what? Restrained molecular dynamics simulation is just solving Newton's second law of motion, just any molecular dynamics uh, protocol that we feed in there the potentials. Those are like hydrogen bonding, van der Waals. Those potentials are there. So we incorporate the potentials from our NMR data as well into that restrained molecular dynamics simulation. This is an added advantage if one can do a restrained molecular dynamics simulation from the best of the generated conformers. This structure can still be made more consistent. I mean, as much consistency as we can have with the NMR data. What are these NMR data? The distance constraints and the torsion angles. Those are the NMR data, I mean, consistency with the NMR data. You know, this is one of the first, by using this procedure, you might be thinking by now, hey, this is a really brute force procedure. It's laborious. Yes, indeed, it is laborious, assigning a protein and then going through all these exercises and determining their distances. Yeah, it is. It is laborious. Nevertheless, this structure was calculated some 32 years ago at NIH. This is one of the first structures that was calculated. This is some protein, antiviral protein from some BDS. Don't worry about that. So that was the scenario. Even when I was a PhD student at that time, we had to do this kind of um, exercises in order to calculate and assign NMR resonances. So as I said, so far so good. If the protein is small, unlabeled means how? Yeah, by now you have already guessed that most of the time we are using only proton. We don't have to label. Natural abundance is just good enough. But so the exercise that we have done so far, that is just good enough. But if the protein grows in size, and then there could be more complexity, then the problems mount, and but with a very limited success we will have if we still continue to use these homonuclear experiments, cozy and nosy kind of experiments, and we try to calculate structure, our success will be very limited. So that's where comes the three-dimensional experiments that we do. And for three-dimensional experiments, we grow these bugs. That means we produce the protein enriched in 13C and 15N. So we no longer have to. I'll finish in about just 10 to 15 minutes so that we can, 10 minutes or so. So the carbons and nitrogens, they're isotopically enriched. That is by growing these bugs or the cells in ammonium chloride, 15N ammonium chloride, and 13C glucose containing medium, where the bacteria carrying the plasmid of the protein, and the protein will be all enriched with 13C and 15N, and then we go to do 3D NMR. Now, just 1 minute, I'll quickly explain what this 3D NMR really means. This is 1D NMR. There is no dimensionality. It's just one dimensional. Here, T1 is just the data acquisition. That means the feed, FID. But in a 2D experiment, you know by now that T1 is the evolution time and T2 is the acquisition time. When there is one evolution time, T1, it is a 2D experiment. We can do this experiment by incorporating, by making a scheme where we have two evolution times, T1, T2, and then T3 is same, the data acquisition. This is the acquisition time. So when we have two evolution times, we have a 3D, three-dimensional data, right? And when we have three evolution times, T1, T2, T3, then we have a four-dimensional, so on and so forth. And same with the unit spins here, each spin will give a 1D spectrum, no problem. But a 2D spectrum, obviously the unit spins are at least a couple of spins, two spins, ij. And then when we do 3D experiments, the unit spin system will be ijk. So three spins can be correlated, all right? And one other thing, and that is what is most important, is that in all these evolution times, T1 in a 2D, T1, T2 in a 3D, T1, T2, T3 in a 4D, all these evolution times must always have coherence transfer going on there. Without coherence transfer, the dimensionality will be reduced. For example, one can just introduce some mixing time or something here, some delay time, where no coherence transfer may take place. In that case, this will not be a 4D or this will not be a 3D spectrum. That means that these evolution times must always carry coherence transfer. So we will use most of these 3D experiments This is one of the, okay, how do we do this? We can combine two 2D experiments to produce a 3D experiment. Say, if we took a cozy 2D experiment, combined it with a TOXI, then we have a cozy TOXI experiment. If the first experiment, 2D experiment, is nosy, the second one is a TOXI, then we have a 3D nosy TOXI experiment. So on and so forth. One can combine two 2D pulse schemes to produce two evolution periods. So two evolution periods obviously means a 3D spectrum. All right. Now, yeah, it's a little quickly. I'll just go over this so that you will know what it means. A 3D experiment is a collection of 2D experiments that are done, or in other words, these are the 2D projections. Each of these 2Ds are the projections of a 3D experiment, all right? Now, these planes can be generated. For example, T1, T2, T3. These are the evolution periods, T1, T2. This is the acquisition time. If we Fourier transform with respect to T1 and T3, then we have a signal that is frequency 1, frequency 2, and there is no frequency. This is still time. This is still with time, but we have frequencies F1, F2. So this is a two-dimensional plane, and as we progress with time, we have these 2D planes stacked up, and the cross peaks in this, or the peaks in these 2D planes, one can again go back to an electromagnetic wave, for example. These vary, their intensities vary sinusoidally. Just the electric wave vector, electric field vector in an electromagnetic radiation that varies sinusoidally. Something similar, that these peak intensities vary sinusoidally. This is actually the basics of in 2D experiment also. Such a sinusoidal variation can be seen. And then this is the third, when we also Fourier transform the T2 dimension, then this is the full 3D spectrum. All right, now where we were there, that what to do when the protein size increases and what can we do, how can we do. All right, one good starting point can be a 2D HSQC experiment. Maybe I'll just check the time. If there, yeah, it's exactly 2:45. All right, fine. In 2 minutes, I'll go over. An HSQC experiment works by polarization transfer from sensitive to insensitive nuclei. Now, this is what we call an inept, and this is what we call a reverse inept. So we transfer the magnetization, and then again we got it back in there. So that's both the nitrogen and the proton here, or the carbon and the proton here. So HSQC is still a good starting point to assign larger molecules the resonance assignment. In addition to this 2D HSQC, we can have a whole battery of experiments called C beta, C alpha, and H, C beta, C alpha, CO and H, H and CO, H and C alpha. These are quite standard experiments. And then these experiments, for example, what are they? For example, say HNCA experiment. In HNCA experiment, the pulse scheme looks like that. 3 channels, proton, nitrogen, and carbon channel. So the coherences transfer, this is the backbone, the coherences transfer back and forth from here to here, from this nitrogen to here, then back, from nitrogen to proton, proton to nitrogen, then back. These are called intra, within the residue, and inter, that means this residue and this residue. So this intra and inter residue coherence transfer with this pulse scheme that produces an agency spectrum. This is a projection. This is how we analyze the data. residue number 59, 60 up to 67, we can stitch them up. This we analyze in a sliced manner at given this. These are the nitrogen frequencies. So this is the carbon proton slice at this given nitrogen frequencies. So we have stitched them up to produce this stretch of residues. Similarly, we can run a 3D nosy distance constraints. You know what? 3D nosy HSQC experiments, they give the side chain resonance as C alpha, C beta, and at the same time, the distance constraints. Just to show you, this is one of the spectrum that we collected. This is a 3D nosy HSQC spectrum of a protein called ATPP16-1. So then, yeah, all right. So yeah, that's the one. And then distance constraints, I said already that 3D nosy and HSQC gives those. And then this is HNC. Am I going down, back and forth? All right. Yeah. So whatever we have done so far, we input those dihedral angle constraints amino acid sequence of the protein, and C nosy, N nosy pick list. C nosy, N nosy will give the side chain resonances as well as the distance constraints and the chemical shift. There's a program again distance geometry calculation, because these are automated, and then we just compute those numbers out. Again, this is the best 20 conformers of a protein called ATPP16-1 that we determined in our lab, for example. And then, yeah, that is the structure. Again, I'm replotting in a different way in here. And then the best out of these 20 conformers is done here after a restrained molecular dynamics simulation, which we do routinely. We have one alpha helix here, you see, and there are 3 beta seeds, beta 1, beta 2, beta 3. We walk from the N terminus, go over, and then come. Here is the C terminus, all right? This is the ball and stick model of the same protein, the 3 beta seeds and an alpha helix. These are the aromatic side chains, you see, and this is what we call space-filled model, in which you see there is a large cavity, a groove here, and as though the protein has appendages. These are protruding out into the solvent. So this is obviously not a globular protein. That is, there is intrinsic disorder in the protein. That is why these appendages are there. There is a hole and a cavity. And remember one thing, if we are very lucky, as if we are lucky in our life, we always, get better things. So if you were lucky, the protein is well behaved, it is easier, I mean, relatively easier. But if a protein is intrinsically not structured, which is 70% of the protein that we harbor in our cells, they are actually not, they don't have, they are intrinsically disordered. Intrinsically disordered structures are usually hard or harder to calculate. So, I'll tell you one thing. All that I have just spoken, it is there. I have written a textbook which is called Fundamental Concepts of Molecular Spectroscopy. It starts from electromagnetic waves, goes through quantum mechanics, goes through all kinds of Raman and vibrational. Eventually, it goes to NMR, the last chapter. A lot of the things that I have just presented to you, those are there in the last chapter. This book will be published by Taylor and Francis sometime early in 2022, maybe in another 4 or 5 months' time. Those who are interested can go over these things. They're written in a very user-friendly manner, as the graduate students and the PhD students should be told about NMR. Thank you very much for listening to me. If there are questions now, I will answer.
Thank you, sir.
Hey,
thank you for
Anuj,
the
how do now I'm not on the screen.
sir,
Am I there?
I'll do it, sir.
Yeah.
Sorry, you need to switch on the video, sir.
My video is off.
Yes, sir. In near to that share window itself, there is a start video.
This one.
Still below, sir. In the WebEx window.
In the WebEx window?
Yeah. Where the mic is there, close to that one, there is start video.
Show active speaker and I don't know. Yeah.
Sir, still down. You need to
Down
go.
in here.
Otherwise, sir, you can escape this presentation.
Yeah.
Yeah.
I've
Now you would
escaped.
see. Now you would see that mute and start. Next to that one, there is start video.
Yeah. It's gone
Yes.
somewhere. Shared, start, post, something like that. I cannot do it, looks like. All right.
Maybe
Yeah.
the
One
video
minute,
camera is
Yeah, I'll do that.
disconnected. Maybe, sir.
Hmm?
Video camera is disconnected, probably.
Video camera is disconnected. Yeah. 1 minute. I'll get out of this presentation if necessary. I'll come back.
Okay.
Right. Oh, it is disconnected. Yeah. 1 minute.
Sir.
Cooking now. Post. Where is this? No. I cannot do
It's
it.
it's fine, sir. We'll go with so you can just keep the presentation on.
Zoom coming. I'll keep the presentation on.
Yeah.
Yeah. Yeah.
So we'll conclude it. Thank you, sir.
Now,
So
if
this,
there's question, let them ask.
I'll just brief it and then I'll open the session for discussion, sir.
Yeah.
Okay, so the today's talk was on the protein structure determination using the NMR spectroscopy, and in this how this correlation spectroscopy has been used for the structural determination is discussed by Professor Abani. And also one of the technique for this for the calculation of this geometry calculations or the distance geometry calculations were also explained as a methodology, and as well as some of the multidimensional NMR analysis of these protein structures also were touched upon. So thank you, sir. So now the session is open for discussion. So if the participants have any questions, either they can type it in the chat window, or you can raise your hand. So that we can unmute your.
Yeah, raise your hands and unmute. That is better.
Sir. Any questions, participants?
No question is better.
Yes, sir. I'm not seeing any questions.
You can ask some simple initial basic questions as well. I'll try to answer.
Yeah, I think the morning also there were some questions on 2D NMR actually. So that if the participants are still there, they can ask.
Yeah, you can ask anything.
Yes, I think there are no questions. So this is the same kind of methodology is employed for this DNA structure determination and all, or they have a different strategy, sir?
The strategy is same. Just they use some little different kind of schemes and other things. Yeah. But to tell you one thing, like as I said, like I mean, to really, let me be honest, to calculate a structure, one doesn't need to be a heavy duty scientist. Maybe a laboratory technician can also do this, because things have been automated and they have been made so much simpler that if we have the starting protein, then this spectra can be calculated leisurely, and then the data can be fed into the computer and the structure is out. But yeah, I mean, sometimes one needs to write a scheme in order to achieve something which he wants to. So there comes the knowledge of NMR. Really.
And Baragan, do you have a question? I have unmuted you. You can speak. Do you have a question? Okay, let me check the question answer. Yes, sir. So there is one question.
Yeah.
What methodology used for polysaccharides structure determination?
Okay, there is something called stereospecific assignment. The procedure is almost similar, but one more specifically goes into the torsion angles, and then the alpha, beta, gamma, like that. But the procedure is not very different. It's much easier actually to do that. One can also use simple 2D experiments like exchange spectroscopy and then NOE buildup, so to determine the structure of polysaccharide. It's much easier polysaccharide structure.
Okay, sir.
Yeah.
Any further questions?
Yeah. I mean, Anuj, any person from NIT Calicut, if they want to come and learn things in our lab or to determine structure of a protein or anything in NMR or in spectroscopy in general, they're always welcome.
Okay, thank you, sir. So the NIT Calicut students, they can think of there is an invitation from sir. So if you want to spend few days in University of Hyderabad, you can go there and learn some of these techniques and come back. So if somebody is interested. So if there are no other questions, thank you, sir. Thank you very much for accepting this request, even though I forced you to give the particular slot and I asked you to give the lecture at that time only. So still you agreed for that.
That you can do. You have that. Yeah.
Okay, so thank you so much, sir. Thank
Yeah,
you for the nice lecture.
it's my
Thank you.
pleasure. Yeah. Thank you
Thank you.
very much. Yeah.
Thank you, sir.
Bye-bye.
I'm handing over to the control room.
Yeah, sure.
Thanks.
It was really an interesting session of NMR spectroscopy. Thank you very much, sir, for sharing the knowledge with us, and thank you for the invitation. The next session will start at 3:15. Participants, please stay online.
Raghotama, sir, can you hear me?
Hello. Yeah. Dr. Anuj?
Hello, sir.
Yeah, you can hear
Yes, sir.
me?
Yeah, sir. I can hear you. Sir, can you just project your presentation so that we can check it and.
So I'll share my presentation.
Yes, sir.
Luckily, today's share is coming up.
Okay, sir.
Okay. Okay. So you see my windows?
Yes, sir. But it's not
PPTs?
the first slide, sir.
This is the first
Oh,
slide.
yeah, first slide. Yes. It's
Yeah.
the first slide. Okay.
So let me try full thing. Yeah, it's changing, no? Yeah.
Yes, sir, it's changing. So you can leave it in the first slide.
Okay. And how do I get my pointer? Pointer
Sir,
options.
options, yes, sir.
There is a pointer. Perfect. Yeah. So we have, when do we start? 10, 15 minutes.
Yeah, in 15 minutes we'll start, sir.
Okay.
So you can leave the first. Okay, you want to close it?
No, I'll leave it like
I think we can leave it. The first slide we can leave it as it is, sir. We can put it in the presentation mode and leave it.
Yeah.
It's fine, sir. Okay. Okay, sir. 3:15 we'll start.
I'll be back in 10, 15 minutes, huh?
Okay, sir. Okay, sir.
Yeah, I'll be back in 10, 15 minutes.
Okay.
Welcome everyone. We can move on to the next session. Our honorable speaker, Dr. S. Raghutama from NMR Research Center, IAC. He will be talking on NMR spectroscopic analysis of peptide structures. The session will be chaired by Dr. Parameshwaran P., Associate Professor, NIT Calicut. Welcome, sir.
Hello, am I audible?
Yeah, I'm ready.
Okay. So let's start. So it is my privilege to introduce our next speaker, Dr. S. Raghutama. He was a chief research scientist at NMR Research Center, IIC Bangalore. He did his MS from Purdue University, USA in 1990. Then he came back to India and did his PhD under the supervision of Professor P. Balaram at Indian Institute of Science, Bangalore. Then he moved back to UK and worked with the Professor M.P. Williamson at University of Sheffield. Then he came to India and worked as a scientific officer at NMR Research Center. He is a well-experienced researcher. He is associated with the running and maintenance of National NMR facility since inception from 1977. His research area include biostructures, NMR method, metabolomics, and so on. He has received several awards and recognition, which include Brooker Young Scientist Award, elected as an executive committee member of National Magnetic Resonance Society, and also he was a life member of several professional bodies, which include National Academy of Science Allahabad, National Magnetic Resonance Society India, Indian Peptide Society India, American Peptide Society, and he has a large number of publications, more than 100. And with this short introduction, I invite Dr. Raghutama for his presentation on the topic NMR spectroscopic analysis of peptide structure. Over to you, sir.
Okay. Thank you for your kind introduction, Dr. Parameshwaran. Okay, at the outset, let me thank the organizers for inviting me to give this talk. So I think the organizers are Anuj and Lakshmi. I've been in a lot of touch with Anuj over the last few days, and especially last 2 days. I had a problem with WebEx, and I also had to take help of Dr. Chindaswamy and I think Parameshwaran and his colleague to fix some WebEx problem, troubleshooting WebEx. So now everything is settled now, so I'm ready to give my lecture. Now, today the session opened very well with Professor Guru's lecture, very good in fundamentals. I'm nowhere near him in fundamentals. You have a wonderful introduction to NMR and so many parameters we introduced there. So it's all helpful. And later on, it was followed by Professor Abhani Bhuyan, who touched the other end. We went straight away into the protein structures and gave a lot of inputs, how multidimensional NMR can be used, structure calculating programs and all. So my lecture would be simply a repetition of this, but in more simpler terms. So let me begin my talk. This is kind of a repetition what you heard already. Okay. And now in my opening slide, we have our NMR. This is the NMR center where we have 8 spectrometers, state-of-the-art 800 megahertz. And my main field of study is peptide NMR, and surrounding that are the few way to tell you how we went about these structures. And my email is there. If you have any questions, any doubts, you can send me an email. Okay. Now, to begin with, this is the overview of what I'm going to talk. This will be in 2 parts, NMR and peptides. NMR, as Dr. Kuru has already mentioned, and Bhani Bunyan also has mentioned, So I mainly touch on 1 and 2D NMR, the chemical shift, scalar coupling, relaxation, NOE, they're more or less covered. I'll just briefly touch it or skip those things. Then coming to the peptides, we have to see the structure layout of that. What is Ramchandran map and how they are stabilized by non-bounded interactions, especially the hydrogen bond. So we take this NMR various parameters and how do we apply them to get this peptide structures. That would be the story of the day. Okay. Now to start with, any spectroscopy is an interaction of electromagnetic radiation with matter. Again, probably this slide was shown in the morning, and concentration for this lecture will be mainly on the NMR. So now NMR and X-rays, yeah. Among the spectroscopy, the NMR and X-rays are the kind of complementary techniques to give the macromolecular structure or any structure in atomic detail. That's more important. You can get information at the molecular level or the atomic level. Of course, there are other spectroscopies, UV, IR, visible, you're all familiar with. But today we are concentrating mainly on NMR. And now, before going to the NMR introduction, as I said, the X-rays and NMR are complementary techniques. I just want to give in a slide the pros and cons of these two techniques. And of course, X-rays is the first one which came into prominence. And the one condition there is techniques developed. The difficulty has been reduced to quite a large extent. But still, the NMR has advantage over there, so there is no problem crystallization. You can simply take the sample. I say soluble because most of the proteins are soluble in water. There is no problem at all. So that way, NMR has a slight edge over that. But when it comes to size, nothing like X-rays. So that there is no size limit at all. Any macromolecule, 5,000 kD, 10,000 kD, whatever it is, even of the size of virus, one can get the NMR, the X-ray structures, whereas NMR has their size limitations. You cannot go beyond certain size. About 20, 30 kilodaltons is kind of the normal of things which are applied. As the size increases, the line width increases, that there are these problems of relaxation rates and all, and you lose your signal before the pulse sequences ends. So that is one problem with NMR. So it has a size limitation. But again, there are methods improved, but on an average, 20, 30 kilodalton would be the kind of limitation. There are, of course, structure solid even as exceptions like 70 kD, 80 kD. Other than that, it's mainly confined to 20, 30 kD. Now, coming to resolution, there is nothing like X-ray structure. It's a wonderful, crystal clear, as they say. Very good resolution. Now, that way, compared to NMR, it scores a point there. But here you get a bunch of structures, not a unique structure. As in the previous lecture, in the Abani's lecture, you showed there is always a bunch of structures. So how well they overlap or the RMS is low, that would be the quality of the structure. But you get decent structures, of course, no doubt about it. But compared to X-ray, X-ray certainly scores a point here. Now, the disadvantage of X-rays is a static picture. It's a freeze structure, or one can say even a dead structure. Whereas here it's a live structure. Really, you can see the dynamics, the real action, what is happening in the system. Now, here in the X-ray, the structures are modified by crystal packing, whereas in NMR, it is actual condition, a physiological condition. Now, when we come to the calculation of structure, as in the previous lecture, Bani was telling you, there are various methods, various software to calculate the structure. So also in X-ray, there are very good automation. When it comes to automation, computer modeling, X-ray scores the point. The automation is very well developed, whereas in NMR, it's still developing. It's not so good. So it takes, within days, one can get X-ray structure, whereas NMR takes. So with that, let us move to next slide. So I don't have to worry about this introduction. It's already been done in the first lecture by Narayan and Kuru. And the one thing I want to stress here is many people get scared when they say what NMR stands for, nuclear magnetic resonance. This is, nuclear scares many people. This is nothing to do with the nuclear energy. Though it is the energy involved in the nucleus of an atom, particularly the proton, the energies are quite tiny. As he was saying, it's in the radio frequency range. The natural radios we hear with Bharti, whatever it is, that is the energy involved. Whereas nuclear energy is billions of times larger. There is no fission happening. So there is nothing to do, or there is no relation to this nuclear energy. One has to be aware of this. It's even better than our mobile phones where we use microwave energy. Okay, so there are a few more details here. Let me not go into those things. It's the energy is in the RF region, which is in resonance with the precessing nuclear, having a magnetic moment kept in external magnetic field. Earlier, it used to be CWNMR. I think NIT still have a 60 megahertz somewhere. I saw that, where you use this electromagnet, and then there is a transmitter and a receiver coil. You sweep the whole range of frequencies from one end to the other end. Either you can sweep the frequencies or the sweep the field. You get an NMR spectrum. It takes about 20 to half an hour to get a normal proton spectrum. Whereas nowadays, something wrong. Nowadays, this CWNMR become obsolete. These are all pulsed NMR. Again, as Dr. Kurur was mentioning, you send a burst of pulse, excite all nucleus at a time, collect the signal as a voltage which is induced in time domain signal, and then use the Fourier transformation to get the frequency domain signal. If it is only one kind of signal, like water, you get one line. If there is a number of frequencies present, it's difficult to analyze manually. So you go to the computers and do this Fourier transformation. You get your NMR spectrum. So now this is the block diagram of the NMR spectrometer. This is our superconducting magnet. Nowadays, it's all superconducting magnet. We have the probe here where the sample gets in, and these are the electronics associated with it, where the frequencies are synthesized. Again, this was discussed in the morning. And then there is this coil, which both acts as a transmitter and the receiver. And when the signal is induced in the coil, they are very tiny signals. So you have a preamplifier very close to the magnet so that this is so tiny, it may even decay in the connecting cable. So that's why you have a preamplifier as close as possible. It'll amplify to a certain extent, and then there are further amplifiers. Finally, a computer controls the whole thing. Now, these are the typical spectrometer, state of the art. This is one of the calendars few years ago, which appeared in our institute. Now, this is the typical 1D spectrum. For small molecules, 1D is okay, but this is a 16. This is because I work on peptides. This is a peptide spectrum. This should be a whole length spectrum. I have cut it into 3 parts and put one above the other. And normally, this is the amide aromatic region. And this is the C alpha region. This is the aliphatic region and all. Now, here itself, the things are quite complicated. So it's kind of difficult to analyze with 1D. So what we do is you pull it in the second dimension and analyze it at the 2D spectrum. Now, the 2D spectrum, it can be homonuclear or heteronuclear. Normally, in this case, it's a homonuclear spectrum. So both axes are the same frequency axis. You get 1D spectrum on the diagonal. So if you project it on one side, you get the normal 1D spectrum. If you project it on the other side, you get the same spectrum. Now, the one thing is, as proton spectrum is very crowded, if you go to pull it in the second dimension, there could be some resolution. And further, as again, I have to go back to Kurur, he was saying To analyze the spectrum, you have to decouple one by one. If there are 100 or 200 peaks, you have to do that many times. Whereas in 2D spectrum, you get all this information in one go. So you can see which proton is coupled to which other proton, whether through scalar coupling, through NOE coupling, so whatever it may be. So all these things are done in one shot, though it may take 5 hours to 15 hours to collect this 2D data. And of course, the 2D data is expressed as a contour plot here. It can be also be stick plot like the 1D things, but it becomes very clumsy, becomes difficult to analyze. So what you do is you look from the top, take the cross sections, it becomes a contour plot, easy to analyze. So that's how they are represented. This is again schematic of 1D, 2D is done. 1D has a one pulse, and this response you Fourier analysis you get. And again, 2D has two time periods. One is called the evolution period, where you don't detect it. It's indirectly collected, and there is a mixing pulse which defines whether it is a COSY spectrum or a NOSY spectrum or the TOXY spectrum or whatever. They defines what kind of 2D spectrum it is. Now here is the COSY spectrum. So you get the 1D on the diagonal. The cross peak tells you whether they are J correlated or NOE correlated and all. And now this is a typical NOSY spectrum. I'm just repeating it again. And now this is the whole the FID collected, and you double Fourier transform, you get frequency domain spectrum. If there is only one peak, like water peak, it's only water solvent, it's of no use. You simply get at the center one peak. Now, if there are two peaks which are not connected to each other, like water and acetone is still of no use because they simply come as two peaks on the diagonal. So it becomes useful if they are coupled to each other like AX spin system, then it not only evolves here, it evolves in the other frequencies also. So you get what is known as a cross peak, which has this information, and normally that is expressed as contour plots. So now here's a typical example of a cyclic hexapeptide. So now let me trace in this one just a valin for convenience sake. Now I have not taken the full spectrum. I have omitted the NH region. I have only the aliphatic region. So now, so there would be a connection to this amide to the alpha, which is not shown here. From alpha to the beta, beta to the gamma, you can walk through this. So if you consider valine, normally alphas come here, betas come around 2 ppm, the gamma methyl comes around 1 ppm. So we can literally trace that alpha to the beta, beta to the gamma. So like this, one can trace the leucine residue. Alpha, of course, NH alpha is there, alpha to the beta, beta to the gamma, gamma to the delta. One can stepwise walk through this. And now one can, that was a homonuclear case, and one can do a heteronuclear on one dimension proton, the other dimension it can be carbon or N15. As Ronnie was telling you, any protein spectrum, this would be the starting point. HSQC connecting proton on the N15. So however well they are dispersed would qualify for further experiment. If they are not dispersed, then they are not structured. Then you have to make some change pH, change solvent, change something to get the structure, and then go ahead and calculate the structure. Now, this is the, as I'm telling you, the COSY spectrum gives you stepwise connection. This is again the valence spectrum given here. But as it becomes complicated, becomes difficult to analyze. So what we do is a modified COSY called the TOXY, total correlation spectrum, where a given coupled spin system, everything is connected to the everything else. So you can take only one part of it, say the amide part, and you get all the information from there itself. I'll show you some examples. And now here, this is a glutathione tripeptide. So now that is a one spin system where these nuclei are coupled to each other. then across the peptide bond, the coupling is not transferred. It stops there. So that's the one spin system. So this is the next spin system. So this is the next spin system. So that there are 3 spin systems which can be easily identified simply looking at the NH and the rest of the connectivity. Looking at the NH to the rest aliphatic region would solve many of the problems. Again, this Gaussian spectrum symmetric about the diagonal. One half is sufficient, the other half is redundant. So now here is again to explain you NH to the alpha, alpha to the beta, beta to the gamma. Now the same thing if you do in atoxy, from NH you can go simply upwards like a ladder. NH to the alpha, alpha, NH to the beta, to the gamma, to the delta in all in one line. So only that region is sufficient to analyze. So it becomes much easier to analyze that. And now here's a typical toxic spectrum. As I said, only that NH region is sufficient. Now, if you blow it up, now this is again another hexapeptide, we can get residue-specific assignments here. Now, let us pull out the arginine first. Arginine, we think, is the most difficult because there is alpha, beta, gamma, delta connection. But it turns out to be very easy because there is specific pattern developed. Now, these patterns are very useful for even computer analysis. Now from NH, this is the NH versus the aliphatic region. Now NH to the alpha, alpha to the beta, beta to the gamma, and gamma to the delta connection one can trace. Now this has a side chain NH also, and one can, that NH also comes in the Zamite region. And now this is a parallel running over there. Now it's from the other way. You can go to the delta, to the gamma, to the beta, and to the alpha. Now here you can see the alpha is the least and the delta is the maximum, whereas in the other case, from the backbone side, it is NH alpha is the highest, the delta is the least. So if you see a parallel line running like that, you can clearly establish this is a arginine residue. So likewise, one can pull up, there is a specific pattern for leucine. One can pull that up. There are 2 lysine, there are 2 such things. And there is this isoleucine has its own unique pattern. So there is the tryptophan has its own, there are 2 tryptophan, there is unique pattern. The only problem here is it can give you residue specific, but it cannot give you sequences. Now, as I said, there are 2 leucines, which is the first leucine, which is the 4th or 5th leucine is difficult to say. So you use a NOSI spectrum to build the sequence across. So together, you can get this residue, the resonance assignment. Resonance assignment is the most important thing in any peptide or protein structure. So if this takes the largest amount of time, it has to be foolproof. You can never go, never do any mistakes here. Because that would lead to wrong results. So make sure that spend a lot of time here, make sure that your assignments are 100% all right, then only go ahead. So now here's simply a cartoon sketch of various amino acids. I just want to say each amino acid is a unique pattern. There's the alanine, that's the valine pattern here, and that's the glycine pattern, and like that I have taken few of them. Okay, so that's about the toxic part. Now, more important for structure determination is the NOE, the through space coupling. Now, what is NOE? NOE is defined as the Chambers alcohol spectrum, and now they can be coupled. They need not be J-coupled, but through it has to be close by. That's all. Now, if you irradiate this CH2 here, you see the intensity change in the nearby proton. So that there is a dipole-dipole interaction. Through dipole, the information is transferred, and you see that a change in intensity. It can be positive or it can be negative. In the small molecules, it will be positive. In the bigger molecules, it would be negative. So it's fundamentally different from the rest of the methods. Very useful method, and currently is the NOE, which gives you the 3-dimensional structure. It's a very important parameter at the point at this moment. And now there are so much structures developed Now people want to try get the information directly from the chemical ship, but this is still far away to go. But at the moment, it is the NOE which rules the roost for structure determination. So it doesn't depend on the scalar coupling, rather depends on the dipolar coupling, direct magnetic interaction. Very important parameter for structures. Okay, now this is the 2D. Just to briefly explain you how this 2D works, we have the first 90-degree pulse. From the Z magnetization, everything is flipped to the XY plane. And now during this T1, it evolves. They are called frequency labeling. During this evolution, every like CH3, CH2, or NH, OH, everything is separated because they revolve around in different speeds. They are all identified. It's called frequency labeled. You identify them, which is which and all. Now, once they are identified, you put another 90-degree pulse tick back to the Z direction. So they are all identified and put back in the Z direction. That is where this magnetic interaction takes place, or dipolar interaction takes place, or NOE transfer happens during the mixing time, which is about 300 to 400, as Adani was mentioning in the previous lecture. Now, this is a very important experiment. Any small NOE is very useful to spend a lot more time because you want to get as many peaks as possible. So now the one problem with NOE is it is size dependent, or so to say omega tau C dependent, because you are working on one spectrometer. Omega is kind of tau C. Tau C is the correlation time. How do you define tau C? It is the molecule tumbles around its own axis. The small molecule, they tumble faster. If it is large molecule, tumble slower. So, this NOE intensity is dependent on the omega tau C. And if it is the omega tau C becomes 1.1, you don't see the NOE. For small molecules, again, Solomons equation, as Abhani was telling you, it gives you positive NOE, whereas proteins with large molecules, it gives you negative NOE with 100% okay. But when it comes to peptides or molecular weight 1,000 to 2,000, it doesn't give NOE. So you have to get these peptide structures, you have to search for other methods. The one thing is, one can use viscosity is a parameter in the correlation time in the tau C. So you can vary the viscosity, vary the temperature, and overcome this problem. Or the best thing is to do a ROSI, which I'll tell you in the next slide. So if it is in the acetone or chloroform, it goes to zero NOE region. You do it in DMSO or DMSO water mixture, where you increase the viscosity, take it into the negative NOE region, and collect it. People have done crazy things. They have used vacuum oil, which is all fluorinated, which enormously increases the viscosity, and one can get a wonderful NOEs in that. And now, as I said, either it would be positive or negative NOEs, but there are some molecules which have both positive and negative NOEs, which we for the first time saw in 1988, where we simultaneously we observed the both positive and negative NOEs, where the whole molecule tumbles at one rate, whereas the tryptophan ring tumbles at a different rate. For the tryptophan ring, you get a positive NOE. For the rest of the molecules, you get negative NOE. And again, these NOEs are very useful for enhancing the intensities of especially the carbon-13, the N15. Now, the best way for peptides which crosses in the zero NOE region would be to do the ROSI. ROSI is nothing but NOSI, but collected differently. So instead of the 3 pulses after the 90-degree pulse, after the T1 evolution, you apply a long spin lock pulse. Now, it holds the magnetization in the XY plane. Now, it's independent of the main magnetic field. Now, the field it's seen is the RF field, which is very tiny, which is in millitesla. So now the omega becomes very much small, or omega tau C becomes very much less than 1, and you all the time get positive NOE. So this is one way of overcoming that problem. You do a ROSI experiment in this case, but given a choice, I would do a NOSI because this ROSI experiment, the TOXI experiment are similar, only the power level and then the spin lock time varies. So the clean experiment, changing this pulse sequences here and all. But given a choice, NOSI is a very good experiment. But if you're held up in the zero NOE region, better do ROSI. Only in that case, we do ROSI and collect the data. Now, here is a NOSI spectrum or a NOSI or ROSI, one and the same. Now here's a designed helical peptide. Again, as one can establish the secondary structures from here. Now the main secondary structures are the helical structures or the sheet structures. Each has a diagnostic NOE pattern. Now in the helical structure, you see the NHS of one coming very close to the NH of the following residue. So one can literally walk through this NH-NH-NOE called the DN-NOE. DNN means distance between I to I plus 1, I plus 1 to I plus 2, I plus 1 to I plus 2 to I plus 3 and all. So like this, you can walk through this, the whole stretch of helix. So what we do is we see this NH-NH-NOE. So for that, our NH-NH is here. So you see large number of NOEs, which is diagnostics of this helical structure. Now, if you blow that up, you can literally walk through this from 1 to 18 throughout the helix. Now here is the 1-2 connection. We know that if it is block protected, the first residue will come most of field shifted. And now the second residue is the AB, which is a singlet. So you have this 1 to 2 connection. And so from there, from 2, you can go to 3. From 3, you can go to 4. From 4, you can go to 5. So you can literally walk through the entire stretch from 1 to 18. So that is how you establish a secondary structure from this NOE. So now, as I said previously, that also because this is sequential information, from toxi you have the residue specific. Together, you can work throughout the sequence. You can establish individually which residue is connected to which other residue and go forward for structure determination. Now again, Bhani showed you this. For helical structure, I just now showed you the NH-NS come close by, whereas if the same structure happens to be extended beta sheet structure, now the DNN goes away, becomes 4.2 or so, whereas alpha N becomes closer. So this is diagnosed as a secondary structure. If you see alpha N NOE, it's a different region altogether, and you can walk through these strands. So we will see that, and now this is taken from the Utzrich's book. So there are various NOEs one can see here, and these are the specific to secondary structures. You can see NOE from first residue to the 100th residue or the second residue, 60th residue, depending on the three-dimensional fold. But these are important for secondary structure. The sequential things are important for secondary structures. Now, in this case, you see this is the designed 4-strand extended hairpin structures. Now there are very few NH-NH-NOEs because the NH-NH distance becomes larger. You see very few NH-NH-NOEs here. It's only around the turn you see that, whereas the alpha NOE is quite rich here. So one can literally walk through these strands by looking at this region. Now, if you look at this region, so now NOE to the NH of the second. So this is the amide region, this is the alpha region. You can walk across this strand looking at 1 alpha to the second NH, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, and all. So likewise, you can go through all strands here. So that's established the secondary structure. So now here's a protocol how to get about the structures. So the one thing is you should have a very good 1D, or for a protein structure, they always use a HSQC spectrum. Make sure they are all clean. There is no impurities, no aggregation. If there are aggregation, diluted and all. So once everything is set, you have to do the resonance assignment, which is the most crucial. Doing the toxi and the NOSI, maybe homonuclear, maybe heteronuclear experiment. You spend a lot of time here. Half the time is spent here, the rest are all book work. Now, here is where intuition is needed. the particular pattern recognition is needed, and it has to be foolproof, as I said. So spend as much time as possible. You can overdo the experiment and get this resonance assessment done. Now, once this is done, you can establish the secondary structures just now explained you. Now, there are other additional NOEs, long-range NOEs. Now, this helps you in getting the three-dimensional structure. Get as many long-range NOEs as possible. The more the long-range NOEs, better would be your structure quality. One can also use what is known as residual dipole coupling, which can refine your structures and all. But the minimum NOEs are needed to get the three-dimensional structure. Now, feed all this information. And in addition to that, you get hydrogen bond information, you get dihedral angle information and all. You feed all those things to the structure calculating program called Cyana, Diana, where you use these constraints from NOE as distance constraint, J values, or dihedral angle constraint, hydrogen bonds, etc. Eventually get the 3D structure. So that is the protocol. Now, here is an example of a bad spectrum. Now, here is a designed 32 residue interlinked helical things, but if you look at the spectrum, it's a horrible spectrum. So now you cannot do anything with this. So now you have to go back and change the condition, change solvent, change temperature, change pH, do something. So now here we change solvent, change the temperature, but whatever we do, there is marginal improvement, there is nothing else. So you cannot do these such kind of structures. So you simply reject it. Now, for a good structure, now this is another octopeptide hairpin where you see very well dispersed sharp resonances. And the other thing is you must have the sequence with you so that every proton here corresponds to a peak here. The same way, and conversely, every peak here must correspond to a particular proton there. So you must have the sequence, chemical sequence present, then only you can correlate these two. Now, there are again defined structures. That is the amide region, that is the aromatic, that is the water, that is the alpha, that is the aliphatic region, metals and all. So now there are various factors influencing the chemical shift, electronic shielding, electronegativity, hydrogen bond, aromatic ring current, so many things, even structure influences the chemical shift. So that is why people wants to, because structure also influences chemical shift. Now there are so many structures available in the data bank. Now there are methods or called the data mining to eventually get the structure straight away from the chemical shift. So I will not go into those details now. Now here's one slide which tells you kind of the chemical shift distribution. Now, normally the C alpha is taken. Others can also, one can also take other chemical shift. Normally, the C alpha in the C alpha range, and if it is a helical structure, you see a upfield shifted C alpha chemical shift. If it is downfield shifted, then it would be a beta sheet structure. So there are some structure information built into this. And there are ways and means of getting the structure from the chemical shift itself. The other important parameter is from the spin-spin coupling. Again, in the morning lecture, it was explained. One can directly get the dihedral angle. So you measure especially the NHC alpha is a function of phi dihedral angle. One can directly, if you measure this chemical shift, one can directly read this dihedral angle, which is very important parameter. Now, this is another contour representation of this. Normally, in the beta sheet structures, you see the J values are very high. In the helical structures, the J values are very low. There is 2-3 hertz. Then you say the phi angles would be helical. If it is 8 to 10 hertz, you say it would be in the sheet structure. But if it is somewhere between 6 and 7, it doesn't have a specified secondary structure. It's called the random coil structure or the loop structure. So also chemical shift has some information on the structure. In the beta sheets, you see very well dispersed both NH and alpha, whereas in the helices, they are all quite restricted. And as I said, in the helices, they are all upfield shifted. The C alphas are upfield shifted, whereas in the beta sheet, they are all downfield shifted. So these are from information to start your structure calculation. One can directly calculate. In peptides, it's quite easy. Simply the separation between these amide gives you the J coupling values of the NHC alpha coupling, which is directly related to the dihedral angle. Okay. So that's about the NMR part of it. Now coming to the protein part or the peptide part, now how these proteins are produced, there are known, what is known as, which I'm not very familiar, it's called centrodogma or molecular biology. So these are all coded in the genes. Now, how do you get that from the DNA? You can get transcript to the RNA, to the here, code for one amino acid. That's how the peptide are synthesized in the ribosome. So they simply, the ribosome is the protein factory where they are synthesized. So the 3 nucleotide code for one amino acid, they simply read this. There is a mechanism to read this, and then they are connected. What is protein? Protein is simply a linear sequence of these amino acids. It's a polymer of these amino acids. So they are all connected. But when this comes out, it doesn't come out as a linear chain. They fold into a 3-dimensional structure. This 3-dimensional structure is very important because then only it can function. In the human system, we have about 40 to 50,000 proteins, having each one has a different function. It can be your hair color, it can be your eye color, it can be your muscle movement, it can be a cancer disease, it can be muscle movement, whatever it is, everything has a protein associated with it. Now, this function depends on the structure, 3-dimensional fold of this protein. So it becomes important to get this folding information. But the tricky thing is, now the whole fold is defined by these dihedral angles, which I show you in the next 5-side dihedral angles. I'll show you in the next slide. Now, each dihedral angle can rotate about 360 degrees, from 0 to 360 degrees. And there are two such things: 0 side 30 to 360 degrees, 50 to 360 degrees. There are enormous space to be covered. It would take an enormous amount of time to fix one particular point, whereas the cell knows exactly how to fold. Within seconds, they fold into 3-dimensional structure. But manually, if we do, it takes enormous time, and that is called the folding problem. And still, there is no solution to it. No, but once we have this fold, we can determine the structure either by X-ray or by NMR, and then that's what we are doing now. Now, to simplify that, the protein structure level can be considered into it. These are all textbook materials, broadly into 4 or 5 categories. Primary structure is simply the polymer sequence, amino acid sequence. Now, these amino acid sequence, certain stretches fold into a helical structure or into an extended structure or into a turn structure. And these are all stabilized by what is known as non-covalent interactions or weak interactions, mainly contributed by hydrogen bonds. And now they eventually fold into a 3D fold. Again, they are stabilized by these non-bonded interactions or weak interactions. Could be hydrophobic interactions, electrostatic interactions, but majority of the time it would be the hydrogen bond interaction. In between, there are what is known as secondary structure motifs, alpha-alpha hairpin, alpha-beta motif, or beta hairpin motifs and all. And sometimes tertiary structure is a quaternary structure. These tertiary structures assemble to a dimer, tetramer, or hexamer, then only it can function. So each stage one can establish. I told you how to establish the secondary structure by NMR. Tertiary structure can be established by these long-range NOEs and all. So let us see how we go about it. Now, as I said, there are mainly 2 kinds of secondary structure: alpha helices and beta sheets. And now this alpha helices, the fifth in this alpha helices, the 5th NH hydrogen bond to the first CO. And in the 310 helix, there is another kind of helix called the 310 helix, where the 4th residue hydrogen bond to the first residue hydrogen bond, and they can be numbered. So now there are 3 residues involved, and the 4th first residue NH hydrogen bond to the first residue CO. Now in this loop, if you count, there are 10 atoms. That is why it's called 310 helix. 13 atom and so on and so forth. So that is about the helices. In the sheets, these strands, across the strand, there are hydrogen bonds, and there are parallel strands, anti-parallel strands. Anti-parallel strands are a little more stable compared to the parallel strand because now here the hydrogen bonds are very linear, whereas this is skewed up in the parallel strands. So with this information, now why structures? Now, as I said, it correlates with the function. For a particular function, particular protein has to pull in a particular way. And even that design becomes helpful. The modeling helps the binding of inhibitors, etc., and compare new structures to the known structure, how things evolve, evolutionary studies. Now, the challenges still remain is how to predict the structure from the amino acid primary sequence. It is said that the primary sequence contains this. So that is how when it's produced in the cells, it knows. Yes, the sequence is given, it pulls into a three-dimensional structure. But if you build synthetically, take randomly amino acids and connect them, it doesn't fold into a particular function. Still, there is no synthetic protein available. I think these days there are a couple of proteins probably synthetically produced. Though you can produce a protein structure, you can put so many amino acids in the sequence, but it cannot function. Now, how do you define this? And now, sequence is always referred from N-terminal, the amino terminal to the carboxy terminal. So this is the amino terminal. The sequence is spread from that and ends up with the carboxy terminal. So now, as I said, it is present in the folding information is present in this sequence. So that is given by Alfinson, who showed that he got a Nobel Prize for this, who showed that the folding information is contained in this sequence. So now that is the linear chain of amino acids, how the protein is built. Now, shape and other properties of each protein is dictated by the precise sequence. It's contained in the sequence, but we don't know. Now, in the protein sequence, if you see this linear sequence, now there are three degrees of freedom. One is across the NC bond called the phi rotation. This is called the dihedral angle. And the rotation across the CC is called the psi rotation. Across the peptide bond, the CN is called the omega. Now, omega has a partial double bond characters, so that is why it is constant. It cannot vary. So this is restricted. Now, all the 6 atoms lie in a plane. So rotation about these planes is called the dihedral angle. So it's mainly the phi and psi which contribute to this structure, and they are called Ramachandran angle. So if we get the information of phi psi, you get the information of the protein structure. Whole protein structure is defined by this phi psi angle. Now, what are peptides? Peptides is simply a fragment of protein. It can be 2 residue, 3 residue, tripeptide, octapeptide, or 23 residue peptide. Could be a cyclic peptide and all. So what is the difference between peptide and a protein? Peptide with a fewer amino acids, about 20, are called oligopeptides. Those with more residues are known as polypeptides. So when do you call it polypeptide or when do you call it protein? Polypeptide specific sequence more than 50 residue are usually known as proteins, but authors define greatly where it starts this term. Because protein, when you say protein, it should have associated with a function. There is a protein melatonin, which is only 28 residues, it has a function. So you call that a protein. But if there is a protein with 50 amino acids, you don't call it a protein, you call it a polypeptide. So those are the definitions about peptides and proteins. And then the protein structure is genetically determined, as I told you now. A stretch of polypeptide chain has no biological function. If you simply stretch it out, there's no function. A striking characteristic of the functional protein is that it should have a well-defined 3D structure. The folding information is contained in these primary sequences. Different sequences fold differently. And now there is what is known as the Leventhal paradox about this. Now, if you take 100 protein, as I told you, the phi side, it can vary from 0 to 360 degrees. Now, consider about 100 residues and consider only 2 conformations for each. Then there are 2 power 100 possible conformations for the protein to fold. So it should map everything here for every possible conformation with 1 picosecond. If you take 1 picosecond possible place, it would take about 10 power 10 years, which is enormous. But cell takes only a fraction of a second. how is it possible? And that is where the Leventhal stated this paradox. Later on, people came out with the inverted funnel model, what is known as inverted funnel model. They said because of cooperative phenomenon in the first few residues, it has to cover a larger space. When they cover, they immediately fold into a native, what is known as a native state. But then they said it's not that simpler. There are intermediate state. Then they say it's still not that simple. There could be multiple intermediate state, and this is the latest definition of this folding. And now that's where Ramchandran comes. Ramchandran was Professor G.N. Ramchandran, who was a professor at IISc, got his PhD with C.V. Raman, then established his own center at Madras, and then came back to IISc. He started our MBU department in IISc, and he worked enormously on this Pfizer. He's the person who gave this Pfizer map. This Nobel Prize work. Unfortunately, he was not given. He worked on many fields. He even gave the collagen structure. That's another Nobel Prize work. He worked on X-ray. He worked on optics. So he worked on Fourier transformation methods. So one of the big contribution is this Pfizer map. It's called the Ramchandran map. Now, when he derived the collagen structure, he also was involved in the DNA structure. By the time he came out with already the DNA structure was already published. Then he worked on the collagen structure. He gave the triple helix structure. And I think some people got jealous and they said the structure may not be correct because of steric hindrances and all. He got a little perturbed and he started to work from the scratch. So he built up dipeptide models and showed that what sterics involvement is there, the energetics of this. Ramakrishnan, who was also a professor there, that was his PhD work. And from this, he showed that it doesn't have to go through all 360 degrees. There are many regions disallowed because of steric clashes. It's only about 18% of the region which is allowed. But these are being flexible molecules. There are what are known as some flexibility allowed. Then they call it generously allowed region. There are three regions: most favored region, allowed region, and there is some little more. There are some more regions allowed called generously allowed region. But still, it is about 25% only of these Pfizer values are allowed. Rest are all disallowed because of steric hindrances. So now this Pfizer map is so important that any structure you do today, as in the previous lecture, Professor Abhani told you that it has to be validated by this Ramchandran Pfizer map. Whatever you structure, you calculate, and from the structure you get these Pfizer values, and now that has to fall within this Ramchandran map, then only it gets validated. Now this is the Professor J.N. Ramachandran, who I have not seen, a wonderful professor, and is one of the kind of pearls of India. And now this is the Ramchandran map. Now, if it is a helical structure, the Pfizer values lie in -60, -30. If it is a beta structure, it lies about -140, -130. And then there are specific regions: alpha region, alpha left-handed, right-handed, parallel beta sheet, anti-parallel polyproline structures, and other specific region which gets its name. Okay, now this is the proof of the pudding. So now this Ramchandran map was developed some 60 years ago, I think. And then when he developed, there are only very few structures, 6 or 7 structures. So when they all fit into this Ramchandran map, he was happy. But literally speaking, there was a concern. There was one structure which was not fitting. So he was worried. And later on, then there was no email and all. They have to be postal mail. Then he wrote to the person who determined the structure and said that there could be some problem with your structure. And then when he looked at it, he corrected the structure. The Pfizer values got well within the Ramchandran map. So that gave a lot more confidence. And this is about 20 years ago, some 20,000, 30,000 structures are available. There are about 48,000 residues considered here. You see all of them lie within this Ramchandran map. Whatever lies out is the glycines, or there are some exceptions where it can take a high energy structure, but otherwise this thing. Now, recently, there are 50 years celebrated in 2013. Jane Richardson, who is a pioneer in this biofield, she gave a lecture, and the title of her talk was The Plot Thickens. Now, there are about lakh structures available now, and if you consider, you see how well everything goes into this. Now, this is the three-dimensional expansion of this Wi-Fi map. And now you see that there are a lot more helical, there are a lot more convergence on the helical structure, whereas the beta structures are kind of distributed. So that is the quality of this Ramchandran map. Now, whatever here is a structure we determined by NMR in Sheffield, and that has to fall well within the Ramchandran map. And now you see it can fall in the favored region or allowed region, but should not fall in the disallowed region. There should be zero in the disallowed region. Whatever you see here, they are all glycines. So that is the beauty of this Wi-Fi map. Now coming to the design aspects, now this is the glycine map. Because there are only 2 protons here, it can cover larger areas except the central stretch here. Now if you replace by one hydrogen with the methyl, it becomes alanine. And normally all these Ramchandran maps or the alanine maps or the rest of the 18 residues except glycine and proline. Proline also can get into this, that's more restricted here. And now if you put replace one methyl, you get this. Or if you replace the other hydrogen, the D amino, it becomes D amino acid, is the mirror image of that. Now if you want to, now if you replace both the hydrogens by the methyls, then it is called the isobutyric acid, abbreviated AIB. Because of steric hindrances, you see the Ramchandran map reduces to a very small portion, because it's a chiral molecule. And now if you remember the Ramchandran map, this is the helical region. Now if you put AB residues into the sequence, you are sure you can design helical structures. So this is the starting point of designing a synthetic protein. So then one can use these constrained residues to build that up. We have built many helices using such kind of things. One can also design the extended structure, but extended structures are normally prone to aggregation. So what you do is you make a hairpin turn. Again, Professor Balram, this is our thesis work. We took about 4 years to develop this. If you put a deproglycine segment, it turns around, it forms a type 2 beta turns around like a hairpin in the plane, and then get extended. And now because of this internal hydrogen bond, there is less chances of aggregation. That's how we can build this extended structures. Now, finally, once you have helices, once you have these extended structures, you can combine them the way you want it and get the 3D structure. But that's all said, easy than done. And now here is a helical structure built by us. Now this is the sequence here. Now the interesting thing here, one can develop by L sequences or by the D sequences. Now you have this AAB residues, you're sure to get a helical structure. And now once you have this structure, there's a right-handed helix. But it is followed by, when we combine this L and the D residues, we want to interested, will it develop into a continuous left-handed helix or the right-handed helix? Now, if there is only one residue here, it would go by the majority of that right-handed helix, because there is a small portion here which the positive phi is also allowed. But if you put another residue, you never know. So what we wanted to do was connect all L residues with the similar D residues, see what happens. Will it be a right-handed? Will it be a left-handed structure? When we did the X-ray and the NMR, it showed that it maintained the first 7 residues, it maintained the right-handed, but the next 7 residues, it maintained the left-handed helix. It's called the ambidextrous, but which is right-handed, we could not do. But looking at more NOE at the connecting region, probably would have come up that by then the X-ray structure came stopped. So, so now this is how the first half is right-handed, the second half is left-handed, and all. So now likewise, one can build the extended structures. This is our first octapeptide hairpin structure. This was the most difficult part to do. And then once we have established this, adding one more strand, if you keep on rotating it, it becomes a beta barrel, it becomes a protein. But what is the use of it? It has no function. It's simply a polypeptide chain, though it can be called a protein. But one can incorporate metal binding sites, induce some functionality into it, and then do. So so these are some variant of that. Now the ultimate goal is to combine these LSEs and the sheets, but the orientation becomes so difficult, you have to work it up. And by the time I had finished PhD, I had to leave, so I couldn't continue. Most important in these secondary and tertiary structures is the hydrogen bond. So let me tell you something about hydrogen bond. The definition of hydrogen bond, in textbooks you see hydrogen bond is sandwiched between two hydrogen atoms sandwiched between two electronegative atoms. So the hydrogen bond covalently bound to electronegative atom is called the donor. Another electronegative atom, lone pair electron, is the acceptor. So there is a bond formed between this hydrogen and this electronegative atom, and that is called the hydrogen bond. But there are some controversies. So IUPAC recently come up with a definition, a form of association between electronegative atom and a hydrogen atom attached to a second relative hydronegative atom. But later on in 2020, there was another brainstorming session, especially in IISc, they redefined it. Now, hydrogen bond is attractive interaction between a hydrogen atom from a molecule or a molecular fragment XX in which X is electronegative, more electronegative than hydrogen, and an atom of a group of atoms, same or different molecule, in which the evidence of bond formation is there. So now this is well explained by Professor Gautam Desi Raju, titled Hydrogen Bonds, a Bond by Any Other Name, Nangyavante Chemi. So, this definition becomes useful because there are other weak interactions, which will show you probably in the coming slides. Now, the strength of this hydrogen bond is quite weak. It varies between 0.5 to 40 kilocalories. But is it a covalent bond? It has nothing to do with covalent bond. Sometimes the strongest hydrogen bond would be stronger than the weakest covalent bond. But hydrogen bond cannot be considered a weak covalent bond. There are a lot of controversies, people saying, yes, it can be considered, no, it cannot be considered, and all. But when we talk of NMR terms, the J coupling is always transferred through the covalent linkage. So people trying to see across the hydrogen bond, is there a J coupling transfer? And they do see some such transfer. People worked on that and established a hydrogen bond through that. Now, there are other weak interactions like CHO hydrogen bond, CH pi interaction. These are all, again, underwent a lot of controversies, but now they are very well established. And for the main structure, all these things contribute. Van der Waals interactions, electrostatic interactions, hydrophobic interaction, these weak interaction. And among all of them, of course, hydrogen bond is the main thing. Now, this is, again, to define a hydrogen bond, it has to be very linear and it's distance dependent. As the distance goes up, the strength goes down. Even the angle is very important. It has to be a linear. NHCO should be linear, then it would be a strong hydrogen bond. As the linearity goes down, the strength of the hydrogen bond goes off. So now these are the various hydrogen bonds in biomolecules. Our concern is mainly in the peptide protein, whereas NHCO are important. And how do you establish that? This is the simple in peptides is very straightforward. These hydrogen bonds can be established by 1D experiment at various, recording the 1D experiment, looking at the amide chemical shift as a function of temperature. Now, here just to explain that, now here is a extended three beta strand structures, hairpin structures. Now they are stabilized by this intramolecular hydrogen bond. And now there are some NHs which are exposed, not hydrogen bonded, outside. Now these are called exposed NHs. Now these exposed NHs can hydrogen bonds to the surrounding water molecule because they are always in solution. So now this water has a hydrogen bonding capacity. Now that oxygen can come a hydrogen bond to this NHS. Now, this is called intermolecular, between two molecules, the peptide molecule and the water molecule. Now, hydrogen bond, of course, is a weak interaction among inter and intramolecular. The intermolecular are very weak interactions that can be perturbed by temperature. Now, when it hydrogen bonds, this oxygen de-shields this proton so that way it moves down. But if you heat it up, it breaks the hydrogen bond. Now, this particular proton chemical shift changes and goes upfield. And that can be monitored by recording a temperature. And now you see this particular proton has the largest slope. Now, these are all exposed NH, they all will have larger slope. I've simply marked only one of them. And whereas this this intramolecular hydrogen bonds doesn't move that fast, though they start breaking, but they need a lot more temperature to break. So that is why you can establish which is hydrogen bonded amide, which is exposed to NHS. The only thing is we don't know these are hydrogen bonded NH to which CO is hydrogen bonded. From the pattern, one has to identify and map that. But that is where they look at the J coupling across this hydrogen bond. That way one can establish that. So that's about the hydrogen bonds. So now with all this background on the NMR and the peptide, I'll quickly go through some case studies in the rest 5-10 minutes. Now I'm taking the example of conotoxins. This is work collaboration with Professor Krishnan, NCBS, and Professor Balram in IASC. Now these are the bone snails, which are very slow-moving object, as you know. But how do they play? They attack that prey. The main thing is the fish. They are very fast-moving. But to their advantage, they have some peptides in there. They shoot these peptides, which is quite venomous, and then they immobilize the prey, and then that's how they attack. And now these peptides, this conus peptide, known to be very good drug molecules. Professor Oliveira, which I show in the next slide, who is the one who worked up with it and then produced two very important painkiller molecules, drug molecules. Now, here's Professor Krishnan, who is very passionate about research, and he, of course, he again passed away a few years ago. He wanted to build a very big conotoxin research across the world, but unfortunately, it stopped. He's so passionate, he himself has to go to the seashore, interact with the fishermen, collect these cone snails, come to the lab, extract these peptides, and work on it. In India, there are about 77 peptide, conotoxin peptide isolated. And now this is the work of Professor Oliveira, who works on this conotoxin, who is again waiting in the Nobel list. One day you may he may get in the coming years. Now, when he collected a large number of peptides, conus peptides, there was a one enthusiastic young student who joined this research group. Now, because he had this, he did a wonderful experiment. He simply injected every peptide to the rats there, and each peptide has a different function. So one had a head swinging, one had a circular motion, one had back leg drag, one was normal, one had convulsion, one had depression. Every peptide contributed to a different function. Now it's the combinatorial effect which these conotoxins have, and that's how they have become so potent. So now coming to our study, we worked on what is known as contrafans. Contrafan is the tryptophan containing peptide. Of course, all these conotoxins mainly are rich in cysteine containing peptide. So we choose contrafan because it acts on the calcium channel. Normally, they reduce this. The one particular thing we choose should increase the calcium channel activity. Now, the pharmacological properties are that the target's variety of ion channels, very potent, very highly selective. They are water soluble, low molecular weight, simple to manufacture. These are 8 to 50 residues or so. Now, how do we go about it? As I showed you, get the crude venom from this conus snails and purify by HPLC, and mass spectroscopy analysis used to detect various the first thing is you establish the sequence and various functional groups. UV, other spectroscopic techniques are used to identify the aromatic residues. Mainly mass spectroscopy used to get the sequence determination along with NMR. So once you get the sequence information, you can synthesize them because these are all small peptides. One can chemically synthesize them. And then the folding information has to be got by X-rays or NMR. And electrophysiology used to do the activity with the ion channels. So this is the protocol we follow. Now consider this contrafan we worked on is called Konus-Larausi, which has a molecular weight of 959, and that is the peptide sequence. It has 2 prolines, 2 cysteines, and one the tryptophan at the center has a D residue. If it is an L residue, it loses activity, but the active peptide has a D residue. So these are all established by various techniques. So the main thing here is, since usual biological increases the calcium current, so that's why we did this NMR. So we collected the NMR data, heteronuclear NMR data, and used this structure calculating program to eventually calculate the structure. Now, the interesting thing was here when the purified peptide was run on a HPLC, it gave 2 peaks. We thought there are 2 impurities, so we cut off this one leg of this and then re-injected it, but again it produced the same thing. Cut off the other leg, again you get the same thing. Then we realized the proline here must be undergoing cis trans-isomerism, which is such a rate that both conformers are coexistent. So now that was established by NMR. We had then got our 700 spectrometer with probe, which increases sensitivity order of magnitude times. And then instead of 8 residues, we could see the NMR of 16 residues. So all NHs, instead of 8 NHs, we got 16 NHs, and so on and so forth. And we could also see that if it is replaced by L omega, it doesn't have a structure. As I said, structure and functions are related only when it is D amino acid. It did get the structure, you got the clean 1D. And because it's difficult to analyze this 1D, we did the 2D NMR experiment. And as I said, this would be the starting point for any protein structure, but this is not a protein still. Because we had the cryoprobe at natural abundance, we can do this HSPLC spectrum, see the distribution, clearly see the red and green are the 2 different conformers of 8 residues each. And then we do this Toxi experiment, can establish the residue-specific assignments. As I said, each amino acid has a specific residue. There's the cysteine, there's the tryptophan. Like that one can establish, but proline doesn't come in the NH region. We have to go to the aliphatic region to establish the proline residues. Now, the one problem here is, as I said, why was it a double conformation? Because of this, one of the proline is undergoing cis trans-isomerism. So normally all these amino acids normally would have a dihedral angle, the omega dihedral angle across the peptide bond 180 degrees because of this partial double bond character. Whereas especially in the case of proline, because both alpha and delta are only protons, it can undergo cis trans. But still the trans are more prominent. The cis, there is little higher chances of cis form. Now there are again diagnostic NOEs to establish that. Now, if this is a cis form, the X-pro bond, the previous residue alpha and the proline alpha come closer, then you can see that diagnostic NOE. If it is the trans form, the alpha would go away. You don't see that, but the delta would come nearby. Then you see the alpha delta. Now, in this case, you see of the 2 prolines, one has this alpha-alpha connection, the other has the alpha-delta connection. So this proline was the cis conformer, this was in the trans conformer. And this was also not only in the cis, the other part is the trans conformer, they are coexisting. So that is how you see 2 conformers. Now you see other NOEs, sequential NOEs, long range NOEs.
I'll share it then. But you need a WebEx. Yeah, okay.
So now there are another characteristic. Carbon-13 chemical shift is established. This the C beta, C gamma chemical shift difference is a diagnostic feature of the cells. Now, with the C beta, C gamma, my time is up. Yeah, I'll just take 2 minutes and wind up. Is that okay?
Yes,
Hello?
sir. Yes, no, yes.
Okay, yeah. Now the trans has a larger difference, whereas the cis has a larger difference, where the trans has a small difference. One can do from the C13 chemical shift also. And now with the NOEs and with the toxin-OZ, one can build the structure using this SANA program. And now you see you have two different structure, one for the cis, one for the trans. These are called shape-shifting molecules. Now this is more efficient way of doing it. The same sequence produces two different structures for binding to two different receptors. That's how these optimized. So we have these two structures defined here. So, and one can further work on this to make it to the drug molecule also. Now, these are all enzymatically, the normal amino acids get cleaved very fast by the enzymes. Now, if you introduce the beta gamma residues, that's the future research, one can stay put for a longer time and then work on drug molecules. So those things are going on. And in the second case, I quickly go through this. This is known as amide precursor protein, which is 700 amino acids. There are again secretases, which cleaves a certain part, and then there is a 42 residues cut off, and then which accumulates in the brain. Now, this has a certain structure due to some interaction. It could be metal interaction, it could be due to some other interaction. It unfolds. When it unfolds, it will start becoming aggregates. Now, these aggregates reaches a certain level, becomes plaque, and these plaques are very toxic to the cells, and then start eating these brain cells, and that's how this Alzheimer's disease sets in. To understand this, and there are various people working on this one. Now, the main thing is the 42 residues. One can break into three regions. The N-terminal region, which has the histidine residues, rich in histidine residues, which normally responsible for the metal binding. The central portion, normally the sheet structure is formed there. And in the third region is the hydrophobic region, which goes inside the, is not that useful for study. So it's mainly the N and then the middle region is useful, but mainly the 1 to 16 residues are used or to simplify the structure analysis. And now this is how this is a cartoon diagram. This has a helical structure to begin with. Due to some interaction, it unfolds and gets the sheet structure and then aggregate form these sheets. Now, the one reason is there is a starting structure. When metal binds to it, changes the structure, and now this change structure are prone to aggregation. That's how it can be transferred. So now, as I said, one can study the center portion, the end and the middle portion, or when it comes to metal interaction, it's mainly the histidine residues, only the N-terminal is sufficient. And now there are a lot of studies done, various metals, zinc is studied by someone else. We studied the aluminum interaction. Now, here everybody thought that it is the histidine which is responsible. When we recorded an NMR, and this is a HSQC spectrum, you see the histidine is unmoved. Shows that it is not interacting histidine, but rather whatever residues it moves here, the blue and the red, there's the movement, they are all charged residues. So we showed that it is not the histidine which is important here, it's the charged residues is important, and we showed the structure, bound and unbound structure, and tell you which are the residues are involved in that. Now, there are many other metals can be studied, copper, iron, etc. And in one study, we took up the copper, the follow-up case, copper being paramagnetic. This is the normal spectrum. This is the with copper, it broadens out, but one can reduce it by adding ascorbic acid. You get sharp lines. But one interesting thing here was it was binding to the histidines here. And now one can do a 2D and see specifically which are the sizes interacting and all. And what was interesting here was when copper was, if you don't have a copper here, this, if you leave the peptide, it starts aggregating. You can see multiple peaks appearing on 54. There's a lot of peaks here. It simply shows that it's aggregating. But when you add copper, you see it never aggregates. So it somehow stopped this aggregation effect. And one can see through the TIM images, this is aggregated. When you add copper, it's not aggregated and all. So there are a lot more studies to be done. I think I'll stop here. And one can also see polyphenol interactions in green tea that also has to show some stopping aggregation effects. And again, this is mainly collaborators of Balram Krishna, Hanimega, and this is the amylite projects were taken in collaboration with MBIT, with Professor Nagendra, Priyanara, and Jagdish, and these are the students, and this is the group we work with. And thank you very much for your attention. Okay, so I stop here.
Thank you very much, Dr. Gautama, for very nice and elaborative presentation on understanding on peptide structure through NMR analysis, which includes some case studies of amyloid, beta peptide, and conotoxin. Thank you, sir. Now this session is open for discussion, questions, and comments. You can write your questions in a chat box. You can unmute and you can talk directly.
There's some questions.
So,
if there are no questions. So,
sir, you can.
Ragutama, can you hear me?
Yeah.
Okay. Permission, you can hear me?
Okay. Yeah.
Yes, sir, you can proceed.
Yeah, Ragutama, it's really very nice discussion, lecture that you gave. I have a question. This
Excuse me, who is speaking? Oh, is Professor Abani?
Yeah.
Oh, okay, tell me. Yeah.
There's when you do a temperature measurement of this hydrogen bonding, do you ever see a de-shielding effect? That means downfield movement of the hydrogens.
When you do temperature.
That's right.
When you do temperature, it will all be upfield shift.
Always upfield.
Because the oxygen interacts with this hydrogen, it forms hydrogen bond. When you break this hydrogen bond, the oxygen moves away. So the hydrogen now no more under the influence of oxygen, it always moves upfield. When it is hydrogen bonded, this oxygen pulls away electrons from hydrogen. That's how it moves downfield. That's my understanding.
Yeah, I also thought so. And I did a bunch of experiments, mostly this HSQC kind of carbon, proton, nitrogen, proton. For one intrinsically disordered protein, I always see downfield shift.
No, wait a minute. No, the one problem could be the aggregation effect. Now, if it is monomer, then this will follow. But in aggregates, it's random because it first breaks the aggregation. Aggregation is again another intermolecular interaction. So when it breaks aggregation, it moves some way. After that, it moves the other way. Oh, we have also seen this if we have this aggregated species, but needs a little more attention to explain that. But in principle, it's the oxygen which D-shields when hydrogen bonded sucks away the electrons from this proton, and then the D-shields. When you break it up, the hydrogen bond goes back to its original position. Okay.
Okay, maybe I'll communicate with you by email. I've been having hard time because nobody in the world accepts what I say for one particular protein. Maybe Mike Williamson himself was probably a reviewer. He gave me a really hard time, but I did not see, deshielding or downfield movement. So I'll speak with you over, maybe I'll talk to you over email.
No, the other possibility is once it breaks, it would be forming some other structure where it is picking up another hydrogen bond. It breaks this intermolecular and picks up. Oh, yeah, and there are some cases where it can be upfield shifted, but the explanation would be the conformation is changing. And then it picks up another hydrogen bond from some other molecule, and then it moves up. Oh, that is a possibility. Oh, yes. Williamson has an elaborate explanation for these hydrogen bonds, structure elucidation. He is the one who even gave thumb rule. If it is below 4 ppb, it's hydrogen bonded. If it is above 8 ppb, it is non-hydrogen bonded.
Okay, thank you for your answer.
Yeah, thank you. Thank you, Anirban. You also have a very good lecture.
Yeah, thank you. Maybe I'll communicate with you by email. Yeah.
Oh, yeah, sure. Any other questions?
Yeah, any other questions? Sir, I have one question.
Yeah.
This is about the intramolecular interaction. So normally the hydrogen bonding interaction that can easily understand from NMR data. Then what about other non-covalent interaction? Let's say cation pi or pi interaction or any simple dispersive interaction. Is it possible to quantify according to your experience?
Like this electrostatic interaction, there are salt bridges. They are electrostatic, isn't it? The charge-charge interaction. One can break that also. But there are more subtle. Hydrogen bond is kind of understood. But one sees this salt bridge interactions as well from NMR. As long as they are breakable by temperature, it is fine. But if you take too much, the peptide itself collapses. Or even the other things is the hydrophobic interaction. These are broadly described, but I don't know how to explain by NMR. There are even this CHO hydrogen bond, which underwent a lot of controversy. How can it hydrogen bond and all? But now they are all shown to exist. But these are all at not quantitative but qualitative level.
Okay, I understand. Okay, thank you.
Okay.
So there are several non-covalent interactions.
Oh yeah, exactly. There are several. Hydrogen bond is one of them, majority of them. But electrostatics, even van der Waal contributes, van der Waal interactions, which is of course again difficult to see by NMR. They all contribute.
Okay. Thank you, sir.
Aromatic interactions, pi interactions, you are saying that they do all contribute.
Okay.
Stacking interactions, yeah.
Yes. So any other questions from audience? We have seen no question in the chat box.
There is?
Oh, no questions. So control room, any questions in the chat box?
No, there are no questions from participants.
So
No, not in the chat window, neither in the YouTube also.
Okay. So if there are no other questions, let us thank our speaker, Dr. Gautama, for very nice and elaborative presentation about understanding on peptide structures. Thank you, sir. Thank you very much.
Well, thank you very much for you all. Okay.
Now I hand over the mic to control room. Hello, Srilaya.
Hello?
Yes.
It was a very informative session covering all areas from fundamentals to advanced. Thank you, sir, for accepting our invitation and giving a wonderful lecture. Thank you, every participant, for your kind attention and participation. Kindly utilize this opportunity to interact with our resource person actively. We are coming to the end of day 1 of online workshop. We can learn to 3 eminent speakers and an NMR